Well, I guess we'll slowly start. So welcome everyone. Start slightly early, but we'll certainly end up slightly late. So yeah, well, good to see you and nice to see that's a packed room. So let me briefly introduce, I won't do it long, but just give you a very brief overview of what's going to be about today. And also let me introduce the people I'm going to, it's a team effort, so I just was chosen to start, but so I'm not, I'm Ludovic. I'm not the only one that prepared some Julia HPC activities for us this afternoon. So there's together with Karsten and Johannes, who is joining remote from the West Coast, and Ivan, who is trying to immortalize the moment. So all four of us, we've set together what we're going to look at this afternoon. So roughly what's just that you have an idea about what will happen next. So we'll get a short onboarding about overview of the computing facility we'll work on, and just a brief overview of how we're going to do it interactively. And yeah, maybe for this first part, let me do a quick just disclaimer. So everything we'll do this afternoon, it's a big experiment, meaning that we'll try to get you all of your folks running on a supercomputer that's on the other side of the world, interactively, Julia on VS Code. So most likely it will fail at some point, but well, bear with us, and hopefully it fails at the very, very end and not at the beginning. Thanks to the effort of mostly Karsten. So yeah, just that you know that this is, well, usually in these workshop things, it's the thing that's not really done, because in classical HPC, one does not really have the capacity, because I guess usually it takes like already the full workshop just to get people onboarded, and we'll try to do this in the, well, first maybe 10 minutes. But yeah, so finger crossed, but I guess that's, if it works out, then that's a good proof that, well, about Julia portability, etc. And that's also what we aim to share with you. Yeah, then actually what we're going to look at. So everything, I mean, HPC GPU computing is really broad, but we'll nail it down to some specific direction because it's what we'll have time to do in 3 hours. So we are looking at well, scientific computing and, let's say, classical HPC in terms of taking what could be CFD-like solvers. So, well, a partial differential equation where it's linear diffusion in 2D, such that we have some graphics as well. And we'll try to play around with that. So it's really concrete. So you know we'll work with a single example, but throughout the whole workshop, such that you're not trying not to be too confusing. So I'll introduce briefly what we will look at, and then it's, let's say, the more well, hardcore part, which is like really the HPC part. And there we aim for not lecturing and little exercises. So it's more like, well, we'll try to motivate what we'll do, but the idea is that during all 3 hours, mostly you will be able to do the hands-on all the time, and yeah, hopefully we get it like rolling fairly interactively as such. At some point in the middle, we'll make a short break such that we can just catch some fresh air and maybe yeah, walk around the wooden pile there and come back and sit. So yeah. Now, well, I hope that all of you are ready with the NERSC account. If not, well, you may get lucky to still get one soonish if you do it now. The good thing is that these accounts, they're active for the entire week. So, I mean, just to know that even if you do something or for some reason it doesn't work out as you expected this afternoon, all the material is online. We are like a JuliaCon the entire week. So, well, if you want to quietly rehearse material, go through example like on your own a bit later on, or fix problems and then do it, you have until the end of the week to have access to the supercomputer, to have access to GPUs with what we'll use with the resources we'll use this afternoon. And yeah, so just that it doesn't shut down at the end of the workshop. Yeah, well, I guess with this I'm done. Is there any practical urgent question of general interest right now?
Actually, if you follow the QR code that he shows, the instructions are there as well. So basically, it's contained in the QR code if you want.
Yeah, and yeah, and I guess most likely, so we'll talk and work. If you're hitting a problem that seems like that blocks you, but may not be of general interest, maybe raise hands, and I guess we can work around. And if it's something that like, oh, obviously that's kind of well, maybe worth of general interest, just feel free to, well, stop us and ask. And if you don't know better, stop us and ask rather than, well, long story short, don't stay in your corner for the entire workshop being blocked on the first thing and not telling anyone, right? So yeah, well, with this, I'll leave the floor to
actually to Johannes.
To Johannes.
So now we are moving to the West Coast, and hopefully Johannes is there. I will stop my screen share. There's Johannes. At least we see you now. Can you try share your screen, please?
Sure. I should have tested that. Okay, one moment. I have to enable something. Excuse me. All right. I might have to drop off and
join again.
Yep,
yeah, okay.
I'll be right back.
Let's hope that this works. For me, it took a second. There he is.
All right. Can you hear me?
Yes, everything works fine.
All right. Perfect. Thank you. I'm going to try sharing my screen. Like so. Can you see my screen?
We can. Let me see if I can put it on even full screen or whatever. How does this work? I mean, I guess it's fine if you maximize your slides.
Oh, yeah.
Like, I mean, we also want to see you anyways, so I think it's fine.
I guess it's fine.
All right.
All right.
So it should come up on your end in a second. Yeah, I can actually see the screen from here, so I know if there's a problem. Perfect.
Interception.
Yeah. Thank you very much, Ludovic and Carsten. And for the record, the west coast of the US. So right now it's 4:37. If I fumble something, that's because I'm not fully conscious right now. All right. So all y'all are going to be using a supercomputer that is at NERSC. So NERSC is a user facility of the US. Oops, can I actually open the... There we go. The NERSC is a user facility of the US Department of Energy. And essentially what that means is we have about 10,000 users that cover every scientific discipline. Unlike other HPC centers that you might come across is that we are what's called a mission compute facility. So our job is not to enable the one code that can run the biggest job in the world, but rather our mission is to make sure that other scientists who are being funded by the Department of Energy are productive. We can't actually go and choose our favorite codes that are best matched with our hardware, but rather if someone comes along with a Python script that wants to call a shell script, that wants to call a VM that runs Windows, if it's critical to their research, we have to figure out how to make that work. So I'm telling you this because if you feel like your corner case is too unusual, or I'm not like the guy who runs Fortran on 50,000 nodes, then don't worry. We are the right place for you. Also, changing slides is a bit weird in Teams, but I hope I figure that out. So I also like to share this slide here because most of our users are actually from the early career category. So if you actually add it together, quick question, can you see my mouse?
Yeah, we can. Yeah, we can.
And maybe if I do like this, it's better. So you should see a red dot flitting around the screen. So if you add together graduate student, postdocs, and undergrads, you get to more than 50%, right? So I like this because it reflects the fact that most academic work is done by the early career folks, but also folks who think, well, the Department of Energy lab, that's only for secret research. It's absolutely not. We are really a place to let folks mainly from universities and mainly from the early career areas to be productive. All right. So the systems that you're going to be using, are essentially the supercomputer, which is called Perlmutter. It's named after Saul Perlmutter, and everything else together. So what that means is that what you'll be running on are these these NVIDIA A100 accelerated GPU nodes, and you'll be having access to pretty much all the other aspects of the HPC center. But the thing that really is most relevant is the Scratch file system over here. And so we're going to be ignoring pretty much all the other aspects of HPC, and we have great documentation if you're interested in learning more. I like to show this slide not to overwhelm you with technical details, but to also illustrate the fact that a compute node is very, very complex. And the whole system itself is pretty much layers upon layers of complexity. The most important thing that from your perspective, will be that you have two different kinds of nodes, right? So, and you'll be using Slurm to decide which kind of node you want. Please, if you're going to use the reservation, I'll show that in a second. If you're going to use the reservation, only use these GPU nodes. The reservation is not for the CPU nodes. But essentially, the system is divided up into two different kinds of nodes. They are architecturally very different. The other aspect that will be very important is that the GPU nodes, this is an example of a GPU blade here. So if you cut it down the middle, you'll have one node here and one node here. The important thing here is you have 4 A100 GPUs that are connected to different NUMA domains of a single AMD Milan CPU. And all of this, of course, is packaged up nicely, and then you have a bunch of racks of pretty much the same thing all over again, held together by a high-speed network. This is pretty much the same thing, but with more technical details. These slides are available in the GitHub repo, so please, peruse at your own discretion. But again, we have the 4 GPUs here, and then we have several network interconnects all routed through the CPU. The other thing that's really important when you run on HPC systems is not only the hierarchy in compute, but the hierarchy in storage. Yikes, I didn't delete this line here. Ignore this. Corey has been decommissioned a while ago. But it's essentially what you the way you should think about these things is you have some engineering trade-offs, and usually what happens is we sacrifice performance somehow. So as you go up here, your performance goes up, but essentially the inconvenience of using this also increases. So you'll be working between the Scratch file system, which is a Lustre file system that is optimized for HPC, and of course, memory, right? But the important thing really is to remember that each one of these has their own unique trade-offs. And I want to encourage you to, again, refer back to these slides if you have to in the future. But your home directory is a good place for permanent storage of code and little like settings and like smallish artifacts really, but and it's backed up, which is great. But it is definitely not designed to work well at scale. Same is true for CFS. CFS and home really give you the same experience, just CFS is for for collaborating with your with other folks on your project. So here we will be working mainly in Scratch. I want to stress the fact that Carsten has done a lot of work to take the tediousness of running things out on HPC systems out, and he's kind of preloaded them on himself. One of the things the choice we've made is to work in Scratch for pretty much everything. Don't do this if this is really production code, because Scratch is purged. We guarantee about 8 to 12 weeks, but we reserve the right to alter the purge policy without notice at any given time in order to ensure the stability of the file system. I can talk at length later if people are interested why. But the point is Scratch is fast, but every so often we go in and delete stuff to make sure that Scratch stays fast. So Carsten will go over how we interact with the system in more detail. I want to illustrate basically just we have SSH. I'll be using a little bit of SSH and then also Jupyter. And the other thing is that we have Slurm for submitting jobs. This is the syntax of your kind of Slurm interaction. So it's either sfetch my JavaScript or salloc and then some options for an interactive node. We will repeatedly cover this. I want to start you early on this though, and again refer to the slides for copying and pasting some of these commands. I will get to some more commands at the very end of my talk in like 1 minute. The thing to keep in mind, the way that this works, the mental model you should have is when you start a job on Perlmutter, it's a little bit like you are going to a head node, which is actually the first rank in the MPI communicator. And then srun, the srun command itself is what actually distributes it across all the ranks. Right, so sfetch and salloc only get you to the head node. So you have to use srun if you want to run things in parallel. We'll be looking at these a lot of the times, but again, a job script is pretty much the command you want to run. We have lots of example job scripts. So you want to run the command, and then all of this stuff are parameters that you're telling Slurm of what kind of job you want and how much parallelism and what kind of resources and all of that. I am going to skip this. It is for it's for your own reference. Carsten mentioned this before. Here's where you find this information again. Go to this URL and use the following training code to get a training code if you haven't done so already. Very important, once you've done this, it shows you your username and password. There is no way to restore these. So please take a screenshot. That's the fastest way of actually just saving this information for future. And I want to also show you, this is really important information to be productive. You want to use now, you want to use the -- reservation equals Julia_training. To use the reservation on Perlmutter that's active now until the end of the workshop. I'll fix this. This was a copy and paste error. And you also want to make sure that your account is ntrain1 and your constraint is the GPU node. If you put CPU here, the reservation won't work. And after the training, you just drop this reservation flag. And I'm basically ending by just showing you what it should look like. So if I want, so I have a job script here, MPI job single node.
Can you increase the font size?
Sure. I'm going to set it to grandpa. How about that? Is this good enough?
Maybe a bit more, and then we're good.
All right. I'm gonna. How about this? Is this good?
It's okay. It's okay. Go ahead.
Okay, I'll make it even bigger. All right, how about this? All right, I don't
it's good.
All right, perfect. Okay, so normally the way you'd submit a job script is you'd run sbatch. Oops, no, this is I'm hoist by my own petard. Let's go. So we would run sbatch, sbatch, and then the job script name. So if you want to use the reservation, which right now is available, so you definitely want to use it, you go -- reservation equals Julia _ training, and you submit that. And the important thing is, give it a second, it's been submitted. With the SQS command, you can look at the jobs that are running, and you should see that the QoS is now resv, right? If it says regular, it's not in the reservation. So if you're stuck in the queue and you don't know why it says regular, it's because you've forgotten this bit here. I don't put them in the job scripts because otherwise the job scripts stop working. All right, that's it. I am going to remind everyone that we have the GitHub repo. You can find my slides in the onboarding area. And also you can, if you're interested in using NERSC in the future, there is this slide deck here, NERSC education resources.pdf, that explain how you can apply for NERSC accounts and explain everything in more detail what I talked about. And also keep looking at the cheat sheet. If we find mistakes, we'll fix them live. So keep looking at the cheat sheet. All right, thank you very much. And I think the next person is Karsten.
Indeed. So let me grab the screen share again. Alrighty. Where are my slides? Oh, there. Okay. All right. Before I start with the actual onboarding in some sense, if this was too fast for you, if you haven't heard of Slurm before, you know, this sbatch and whatever, we will guide you through this. Like the job scripts are prepared for you, right? Like this was just to give you an overall picture of the story, right? The cheat sheet has been mentioned. So under help in the repository, you will find two cheat sheets, in fact, one for Perlmutter, one for VS Code, where I just try to put every command that is like super useful in there, right? Like the most top 5 commands or whatever that you need. But once again, the instructions should be clear enough so that you hopefully never have to look at it, or even if you have to look at it only once or whatever. Now comes the kind of actual onboarding. At the end of this, we will actually do something, unless you've already done it. But I want to start with some general notes, how you run Julia and VS Code on Perlmutter, or more generally on other clusters as well. There are some things that are very common that you have to take care of. And yeah, we'll do this together now. Once again, all the slides, all the stuff is in the repo. So how do I actually get with VS Code to Perlmutter? You know, first things first. And the easiest thing is that, you know, VS Code has this remote SSH feature. So essentially, if you can SSH to a cluster, you can run VS Code on the cluster. This works great, and we'll do this together later, so you don't have to do it right now. We'll do it in 5 minutes. It works. You just put in the host name, enter your password, and there you go. That's true for the login node. Sometimes you want to work on a compute node. So login nodes are the nodes that you use to enter the cluster in some sense, and compute nodes are, you know, the beefy machines, thousands of them out there with GPUs and all the accelerators of various kinds. Sometimes you want to be with your VS Code session, like the entire session, have it running on the compute node. So similar as the VS Code session is locally on your laptop, you want to replace your laptop by this compute node so that you have everything available. The Julia extension works and so on. This works with SSH proxy jumps. It works for NERSC full accounts. Unfortunately, it doesn't work for training accounts, right? So it is related to multi-factor authentication and whatever. So no way I can make this work for you guys. So I might jump on a compute node with my session, maybe demonstrate this. You will work, at least in that sense, on a login node. And if you need to go to a compute node, you will do it the regular way, either submit a job script or, you know, go there with a terminal. We'll describe this. So I promise you it works, but it doesn't work with training accounts. By the way, there is a way to also make it work with training accounts, remote tunnels. I included this in the slide deck. So if you are super curious and looking for an adventure, you can go down that route. But once again, not for the general audience here. Julia setup. Which Julia should I use on a cluster? The general story is essentially regular binaries, right? You don't have to compile Julia from source unless ... There are some cases, but 99% of the times you don't have to. The cases could be something like profiling with a specific profiler, or using profiling the C part of Julia or something. So generally, you just want regular binaries. So either you wrap them yourself with Julia up, or download them from the website, or on most clusters these days, there should be a system module which already has the binaries plus some extra stuff. And that's the case on Perlmutter. So Perlmutter provides a module. You don't have to remember this command because the magic will make this work. But before I introduce the magic, I will show you how it's done. So we have to load a certain module part, and then we can write module load Julia. And this will not only make Julia, the command, available in the terminal, but it also adds some extra sauce on top. And this extra sauce is it can help you with packages. So the extra sauce could be that it sets some preferences such that when you in your environment then add MPI or add CUDA or whatever, it automatically knows what it needs to do under the hood to make it work. For example, this is a Cray machine. The standard MPI JLLs that would be downloaded if you just add MPI, they don't work on Perlmutter. But because of that extra sauce, everything works without you even noticing. You just do add MPI as you always do, and under the hood, it works. So we will use this one. Put the Julia depot on the parallel file system. So we've heard a little bit about file system. So we will put the Julia depot, that is this .julia folder, we will put it on Scratch. And why do we put it on Scratch? First of all, Scratch typically has high quotas. So, when it comes to number of files that you are allowed to have, the size that you are allowed to have. If you put it in home, on most clusters, not all of them, you will get at some point quota messages, and make your admin, I don't know, hate you. Also, it's writable. Not every file system in the cluster is from within a compute job writable, right? And the Julia depot needs to be writable. Julia wants to write log files and whatever. So you need a writable file system. And there's no backup of redundant data. Everything in .julia is reproducible, right? You can just get it back. It's just package data and whatever. There's no code in there from you. So why would we need to back it up, right? Like space is costly or backup is costly in some sense. And we can use Julia depot path, the environment variable, to tell Julia where the depot should be located or where it should look for the depot. As Johannes mentioned, watch out for automatic deletion, because Scratch is typically purged every once in a while. So that means depot gone, okay? Once again, typically this happens every month, or different centers have different rules for that. You can work around with this by just touching the files periodically, just making the system think that you've worked on all these files. It's not recommended officially, so I hope this talk doesn't go on YouTube, I think. The other thing is, once you are on VS Code, you've set up Julia, you use your system module, and you have put the depot on Scratch. Now you want to use the VS Code extension, the Julia extension that you use on your laptop as well. You can install it easily, and we'll do this in a second. However, it doesn't know about this module story that I shared with you on the last slide. So you have to teach the VS Code extension to first load the module and then run Julia. Otherwise, the Julia command is just not available. So there is a Julia wrapper in the workshop directory which does this, and you will use it in a second. So having said that, let's do it. Let's actually do it. So let's run VS Code on a Perlmutter login node. So do this now. Open VS Code on your local computer, and then press F1 or whatever, or Command-Shift-P, so that you get this little input prompt in the top, and then execute the remote SSH open SSH host command. And then you should, I'll demonstrate this in a second live. Yes, sir. Yeah. Yes. Yeah, so I wrote this in the README as well. So I will so in the everything I'm sharing now in more details with all the steps explicitly laid out is in the README, in the starting README of the repository. And I believe if I not erase the comment, I put some comment there. For some VS Code versions, this thing isn't installed by default and so on. So if you don't have that, install the remote SSH extension or whatever SSH official by Microsoft. But for most of you, for all, if you just download VS Code from the website without any fanciness, you have that included already out of the box. You do. I tested it. You don't? You just downloaded it? Okay, then sorry. Okay, then if that's the case, I apologize. Then install the remote SSH extension. So, go to the extensions on the left. It's, what is it? Command-Shift or Control-Shift-X. And then search for Julia for remote SSH and press the thing that has Microsoft written behind it. Once you have that, use that command. Then enter this host. So your username, x_perlmutter.nerf.gov. Obviously, train XY needs to be replaced by your username. So I don't know, train 75 or whatever the number is that you have. Might be 3 digits, I don't know. And then there should be a pop-up that asks for your password. You enter your password, you press enter, and hopefully after a second or two, you should be on the node. So let me do this actually. And actually, let me do this with a training account myself. So here's my VS Code. And now I say connect to host. And now I say training account at perlmutter.nurse.gov. And since I have no clue what the password of this account is, I have to look it up somewhere. There you go. And I was too late, I think. Oh, no, there it still is. Right. And once you've done these steps, VS Code should have you on the Perlmutter login node. So at the end, it should say something like train whatever at login whatever, right? There are multiple login nodes. All right. I hope most of you have reached this point. Yeah. Oh, you have a problem? Yeah, if it's individual, then let maybe Ivan can help or whatever. Because if I walk to everyone, we won't get anywhere, right? All right. Assuming you have managed to do this, let's move on. And that is the on Perlmutter part in the README. So what we now need to do is clone the materials, right? The repository. We want to have it on Scratch in that folder that I mentioned here. In there is a file setup.sh that you want to run. And then we want to point the Julia extension to the Julia wrapper for the reason I mentioned before. Once again, take a look at the README in the repo where I have really told you every command that you have to press and, every... Like I try to make it as explicit as possible, and Ludovic was my test earlier, so for him it worked. So let's hope for the best. And yeah, actually, let me do this live as well. So, that's the wrong window. Need to go here. So actually, let me look at the README myself. So here's the git clone command. You just copy it. You run the git clone command. There you go. Then you cd into this. It's written in the README, but I know it by heart. So you just go into the folder, which is now on Scratch, which will be different for all of us because it contains the train whatever information. Once you're in there, you run the setup part. Let me just make sure that exactly. You run the setup part. So setup.sh. And what is this doing? This is the magic. But the magic that I've explained to you, at least mostly. So what this does is instantiate the Julia environment, which should be free because I prepared an environment depot already, which has everything precompiled. If not, doesn't matter. It installs some MPI wrapper that we will use later. It installs a Jupyter kernel in case we need it. But there's not much magic in there. Feel free to look at the file. It's like, I don't know, 20 lines of code, not even. So although we have some magic here, I want you to understand at least the basics of it. All right, once you have done this, essentially you're good to go. The problem is I've also modified your Bashar-C to put the depot on Scratch and so on. And your VS Code doesn't notice yet because we started it before I changed before we made the changes to the Bashar-C. So what you have to do now is kill the session, just quit VS Code. It's the easiest thing, just kill everything, restart VS Code and connect once more to the cluster. No, because the thing is, VS Code itself doesn't know from the BashRC. So in the terminal in the bottom, you can obviously do that, and you would have the changes, but the VS Code itself doesn't. So if we install the extension in a second, they don't know it and so on. I only figured this out by testing it myself. Like, obvious mistake that I made myself. All right. So anyhow, I wanted to connect again. So I have to remember again what this account was. So, just a second. Let me just quickly log in, and then I'll take your question. There we go. And for those of you on YouTube, the password and the training account will be offline after this talk. So sorry to get your hopes down, I guess. Yeah, there was a question somewhere. Yeah. Yes. Yes. Well, kind of. So first of all, the question is, so the participant said that they have, run VS Code on the cluster before, and then they log off and log on again a day later or whatever, and at some point they realize, oh, there are multiple VS Codes server processes running on the cluster on the login node. I don't have a good solution for it. Sometimes I just kill them. I mean, you can just kill them. They will restart as soon as you log in, so no issue with that. But that brings me to a more general point, and that is this system has multiple login nodes. I don't even know how many Perlmutter has. And if you end up, and you don't choose the login node here, right? You get randomly assigned a login node. So whether you are grabbing one of your existing VS Code server instances or another one is sort of not in your cards. On most systems, I recommend to, if you use VS Code on the cluster, choose the same login node all the time. On Perlmutter, you can't. Because they won't let you pass the load balancer. At least I don't know the way. Yeah, but yeah, I don't have a better answer than killing this. Yeah. And getting back to the script. So now we are on a login node once again, hopefully with the BashRC changes reflected in our session. Now we want to install the Julia extension. And so you just open the extension or Command-Shift-X. Once again, the command is written in README. You search for Julia here and you install it. And just to be clear here, we are installing this on Perlmutter now, right? This is not our local. We are not installing this on our laptop. We are installing the extension on Perlmutter. So once we've done this, I have to look at my script. What is supposed to be done next? Oh, yeah, pointing everything to the wrapper. So what you want to do is you want to copy this path here, go to the VS Code settings, click on this remote tab, right? This is my local settings. These are the remote settings. I want to go here, then search for Julia executable. And then here in the executable path, you put in the path that you have copied from the README, once again with trainxy replaced by your username. Okay, so if you put trainxy there, nothing will work. And for those of you who have already followed the instructions before the workshop, I made some half-an-hour last-minute changes, like half an hour before the workshop. So you might want to git pull. I mean, I would anyways recommend you to git pull the workshop materials once more. There was a bug in this Julia wrapper, which only appeared for some accounts for some weird reason. Yeah. Sorry? The extension, you mean? Okay, maybe you can check. Yeah. Okay, but once you've put this in there, like this wrapper, essentially the extension should work. So now you should be able to press Alt-J, Alt-O, or Option-J, Option-O, or run the start REPL command explicitly here in the input prompt. And hopefully you will have an interactive session, maybe some pre-compilation, whatever. And then hopefully you will have a REPL running on the cluster. And while this is going on, let me once again explain exactly what's happening here. The REPL that we just spawned with either the command or start Julia REPL, this is the integrated Julia REPL, the one that talks to the Julia extension, right? Where you can do inline evaluation. You need this connection to get plots in the plot pane, all of that magic. Whereas if you would just use a regular terminal and start Julia there, which you can obviously also do, this is not connected to your VS Code, right? We will use both as part of this course because, you know, sometimes we have to go to a different node and then, you know, but I hope that makes it clear. So this is the integrated REPL now that works fine. And last but not least, now we have the extension working. We have our, so we are in Perlmutter and everything. And now what we can do is we can go to what do we want to do next? We have everything. Oh yeah, last thing last. So what we want to do now is I kill that REPL. I don't care about it. You want to open the folder, right? Like the workshop folder. Currently on the left, you don't see any files there, right? The manual way is to click on open folder and then just, you know, put in the path, like the scratch and then whatever the path is. The easier way to do it, in my opinion, is in the terminal in the bottom, just cd into the folder, scratch, JuliaCon 24, whatever, workshop, right? So, okay, it auto completes it. It's called, that works for all of you. Like if you write it like this, cd into that, it works for everyone. And once you are in that folder, you just type code -r and a dot. The dot is current location, -r means reuse the current window. And if you press enter, VS Code will automatically open that folder for you. I find this easier than to type the path manually up there. But either way, once you've reached that stage, that would be like, it would be great if you could reach that stage. Right now, what do we have? We have VS Code running on a login node on Perlmutter. We have the folder available, all the files. We have Julia working, so we can spawn the REPL and everything. We see plots in the plot pane and all that jazz. Right. I hope this worked for most of you. Take some time if you need it, because once again, if you can't work on a cluster, you will get some issues later on. Some general question, yeah? Well, so the depot, you mean, like the .julia? Multiple reasons. First is, it's good to have it on a parallel file system. If you go parallel with MPI and so on, it's better to have it there. Actually, if you go super parallel, like saying, I don't know, thousands of nodes, you run into other issues. We can talk about this later. But there are also quota issues on other file systems, right? If you would do it in home, forget about performance. You at some point you install all your favorite packages, and at some points you get emails from your admin. I mean, typically first as a soft quota and then a hard quota, and then at some point you can't do anything anymore in home because of the quota. There are multiple reasons to go away from home. On the cluster that you use, you know, for your, you know, outside of Perlmutter, it depends on what you have available. Clusters are different, but typically home is not the place where you don't want to have your Julia depot. Okay. Module load. Yeah, this module stuff is generally how software is managed on clusters. So imagine there are, I don't know, 500 versions of every software that you can imagine, 20 versions of Julia, 50 versions of MPI, whatever. You want to differentiate, you want the user to be able to select between them, right? And this module system is exactly that. So you could say module, MPI, you can even put a slash in a version number and whatever, and then basically the user can compile in a job script the environment, the software environment that they need. Exactly, mostly, yeah. All right, I hope all of you have reached that point. Let me go back to my slides because I think I'm running out of time. Jupyter, if for some reason this doesn't work for you, this entire VS Code story, I think you should do it because that's how I mostly work on a cluster, or maybe with a pure terminal approach. Rarely do I use Jupyter like as my production system on a cluster. But if you want, there also is a Jupyter for NERSC, right? So that's kind of what we call here the fallback option, right? You click on it, you click on give me a node, like you enter your credentials, log in, give me a node, and then you are on Perlmutter as well with the Jupyter instance, and then you can also go to Scratch, go to the directory of the workshop, and then run Jupyter notebooks in there if you prefer. But once again, I would say this is the fallback for today. And by the way, you can run Jupyter notebooks inside of VS Code as well, right? So in fact, we will do this for multi-threading, for example. There will be under parts multi-threading, there will be a notebook that I will just open up in VS Code. Yep. Yes, depends. But yes, so I mean, okay, first of all, a little disclaimer. I work or used to work at an HPC center, so I have lots of privileged access. So for me, it's just, why wouldn't I work on some node on a cluster? Why would I make my laptop heat up, right? So 99% of the time I develop on a cluster. Yes, that's obviously the question you're aiming for. Should a regular user do? Depends on the cluster, the rules, and so on. Working on lock-in nodes, fine on some clusters. You get angry emails on other clusters. If there is a development node available that you can get interactively, depends on the system. So, you know, the HPC centers I work with, there's a way to get an interactive node pretty easily without waiting for, I don't know, 20 hours. But it depends. Like the answer is depends. But for simple stuff on a lock-in node is typically fine. Yeah. Yeah. No, actually, I've been told that on NERSC you can work on a lock-in node pretty freely. Like they even have, I mean, you can use it, but they even have an A100 in lock-in node, in every lock-in node. So, so yeah, I mean, obviously they also have money, right? But yes. Okay, anyways, let me stop here. And I hope I didn't carefully check my time, but hopefully Ludovic isn't killing me. And by the way, I saw the coffee break notice. I thought that was at 3. Is it earlier? 2:30. I see. Okay. So then maybe you can finish in your part, or let's try this. So we switch up. So now we see the example. So now Ludovic will introduce the example for today, like the problem, the physical problem, very briefly. So we will make a switch here.
computing, you'll see a bit later on. And the second thing is that it's kind of so GPU computing, it's very efficient, and also for parallelization. So what if we want to go beyond one computer, like have like a supercomputer where there's like many nodes, so many computers wired together? Then one will need to exchange information, and having finite differences, a regular staggered, like a regular grid, Cartesian grid, simplifies greatly the thing, and that one could, for example, do more complex things afterwards. To make the scheme stable, so still there is, well, some fanciness, meaning that we'll use what's called the staggered grid. So that's what's drawn here. That's our computational grid with the finite difference cells. And basically the green dots is the cell center. It's where we have the quantity C that will be defined. So you can imagine really every cell has a center, has the quantity C, like the let's say concentration of syrup. And then we have the fluxes in the two spatial dimensions. So we're looking into these things. So the X flux and the Y flux. And well, naturally the flux, so you can, if you recall, if we look at the PDE, so the staggering makes some sense because we have the quantity C in the middle. And then if we take the gradient or the derivative, so if I make, well, C here minus C here, I get a gradient, and this gradient is, well, at the boundary between the two cells. So it also makes sense that it's physically located there. And then, well, if I want to update my concentration, I can take the gradient of the fluxes, which also makes sense in the spatial layout. So, but this results in a kind of a non-regular, well, in this kind of asymmetric grid, kind of, because quantities have different spatial location, meaning arrays that would hold these quantities will have slightly different sizes, just to keep in mind. And I mean, later on, if it's confusing, you can go back to that image because that's really how it is. For the setup here, I decided on some non-dimensional quantities. So basically, we'll have a domain size of 10 and a scalar linear diffusion coefficient of 1. And then, well, we can compute the grid or cell size, which is the length of the domain divided by the number of grid points. And S are the grid points in, well, we have the same X and Y direction here, just for simplicity. Our initial condition is this drop. So it's like concentration, let's say, and I just dropped like syrup in a square glass of water view from the top, basically. And where it's red, it means like concentration is 1. Where it's blue, blackish, it means there's concentration is 0. And over time, we expect this drop to spread. So let me give you a brief overview on the structure of the code that we look at once, and then most likely what we look here now, we won't look at anymore, and it will be somewhere in a file, in a shared file we'll include, because it's something that won't change throughout the entire workshop. So open it here. So the code diffusion to this, so it's in, if you're on, it's in parts, diffusion 2D, and then there's the diffusion 2D code. The notebook I'm working from is this one, if you're curious. I'll just hide it for a space. So that's what our code looks like. So this is our starting point. It's a plain vectorized Julia code. It, well, uses a plotting library. It includes some definition in this shared that I'll go over. Then we define some compute function, and we have, like, say, the main, so the action function of the script. Let me just pull shared. So there we basically init the parameters. So it's like the length is 10, diffusion coefficient is 1, this the S, the time step, that's the CFL condition, some range for plotting, and frequency of output, basically. That's all what's there, and And in these files, we have just various flavor of it for the different implementation, but that's the knowledge that's hidden away, let's say, because that's our physics and initial setup. So if we take things just in logical order, so what we want to do, we want to run our script with a given resolution, a given number of time steps, and decide if we want to visualize or not. This would go here. So we initialize, we get the parameters that I was just showing before, which are initialized. We initialize these arrays, so concentration and 2 fluxes. Maybe just let me pull you here. So that's my Gaussian parametrization that I put to C of size nx and s and s. And the fluxes, since they're staggered, there you can check on this checks out the drawings, so they're shorter in these different directions because of the staggering. And then so basically I do these initializations here. Then I can initialize the figure, and then I have what's called the time loop. I have my action loop where I will make the physical prediction of diffusion, right? So there I call 2 compute functions. First, I want to compute fluxes from concentration, and then with the new fluxes, I can compute concentration with the divergence of the fluxes. So these 2 lines correspond to the 2 basically equation here. So this is compute fluxes, and this is compute diffusion step. So the compute fluxes is literally the flux is minus diffusion coefficient derivative of C over d x or y. Here it's the same, and the same thing in the y direction. And then the update, these taking not the full array, so doing some special care with the boundary values. This is because of the staggering. Like again, if you do it like it checks out with the drawing. So I can only, because of second order PDE, I can only update inner points here of my concentrations. I would need boundary conditions that are explicitly set to 0 because we don't touch the boundaries here. I can update concentration with the derivative, the divergence of the fluxes. That are my 2 compute functions. And then I can, if I want, update my visualization at a given frequency that can be set with this n-out parameter. And yeah, so if I execute the code for you as well, if you can execute that code, so you see it kind of, well, it would make animation. It's kind of depending. Sometimes it's a bit like there is some lag, but so I fix the color bar to the initial condition. So if I would pass here like, so if you put NT or less, then it diffuses less. And if I put it like to 5,000, then it would just diffuse further, like diffuse more. And at some point, it would just gray out the thing. Like I have a glass of syrup I can drink. One last, yeah, just one thing. So
you will get some time after the break.
Yeah, well, one last thing, and then we can go for a coffee break. I'm told it's like, so the code also has some timing, so some performance measure, meaning that, well, after skipping 10 warm-up iteration to account for various things, I start my stopwatch, and at the end of the computation, I check the delta t of when I started the stopwatch minus now, and then based on this delta time, I report timing and something that's called effective memory throughput that will have a look right after the break. So yeah.
How long is the coffee break supposed to be? Half an hour. Oh, okay. That we planned differently. Okay. Okay.
Yeah. Well, then, so there is coffee break that wasn't really planned in our program.
I mean, we planned something, but not for half an hour.
So
but maybe we can ask, do you prefer to just stick with a long coffee break and then maybe we'll run late? I mean, you can leave obviously, or do you want us to cut the coffee break short? Any preference?
So who is for shorter coffee break? Okay, good.
All right, that's it. I don't think we have to ask the others.
Good. So let's
do 15 minutes.
Can you come back we start again in 15 minutes, right? So, well, yeah, kind of 2:45 plus 2 minutes.
Actually, I only learned about the coffee break, that there is one at all. I learned about it yesterday. And I just checked the website, and that's why I was confused when it is. Yeah. No, I mean, it's no need to make the best out of it. We're doing it in some way, like, yeah. Now it's fine. Okay. So let's, actually, I will just let my laptop here and let him run. I mean, I'll stay here anyways for the 15 minutes. Well, I think we are, like, except for the coffee break thing, I think we are rather well in time. Like,
So guys, we'll leave it here, but if you want, you can put it mutes if you want.
yeah. You forgot to mute us, maybe?
Yeah.
And only 1 hour left or whatever. What the heck?
This ice, it's got to be.
All right. I think at some point you have to step aside. We'll be back at time, everyone.
I guess we just need to restart.
So it's mid-90s and it's an upward trend. So I have no idea if it's easy to get started with it.
You think the
You know, maybe at 50. So we told them 15, so we make it 20, right? So start at 50 and then no one can complain.
Why?
I guess we need to restart.
We need to start with.
Well, we can chat just later. Yeah, sorry, we need just to.
Maybe now it feels like people are quiet. Unmute. Unmute?
Yeah.
Many people recover the problems.
So just out of curiosity, like if I guess we start in 30 seconds, did some of you try to run this simple diffusion 2D code in VS Code, obviously running now on the login node on Perlmutter? Does it work? You get the visualization? It's super. So yeah, that's kind of the. Yeah, well, if you, yeah, true. If you want, so there are like 3 ways how you can run the script right now. So assuming that this is like that you all have just that you followed Carson's instruction and that this is now, you can see it down there, it's VS Code running on Perlmutter, on the supercomputer, on the login node, and the Julia that's here, I didn't type Julia in the terminal. It's the Julia that opens when you make this Control or Alt J-O, like in the instructions, such that you get the visualization.
You got to share the screen, I'm told.
Yeah, well, that could well be. Thanks.
Camera is good. Just share. Yeah, now it works. I think it works.
Yeah.
Yeah. So yeah, there are 3 ways to run the script. So the first is to hit the play button up here, and that would execute the script and report it. The other option is to go in the terminal. Well, you see it down here. It's to type include brackets hyphens, give the name of the script. However, one has to make sure that that it's on path. So yeah, well, I need to find where it is. So then so that's basically where my script is. So I can include. So I need to point it to, depending where I am. And then if I run that, it would do the same. So it would include the script, run it, and produce the output. And the other, what's this thing also here? The last option is there is a shortcut, like on Apple is Shift Enter. I guess it's the same maybe on all architecture. So if you're in the script and you hit Shift Enter, it would execute line by line or function by function, and you could go through the entire script and it makes these check marks. So that's a 3. The easiest one is just to hit the play button. I need to install.
I can.
Yeah, Carson can check. So yeah, well, now just to finish a bit, kind of to set what we're going to use and what we're going to look at. So you see the script reports 2 things. It reports time, which is the wall time, which is, well, the time in seconds from where I started the timer, so skipping the first 10 iterations until the end of the iterative loop. And obviously, if I increase the number of iteration, it would increase this dwell time. The second thing it reports is a metric called T effective in gigabyte per second. And let me just 2 minutes talk about that to introduce you to the concept. That's kind of, yeah. Oh, okay. Okay. So to introduce you to the concept, basically, so performance, it's another entire other topic, and there are various ways to measure performance. So, well, if we had more time, we could screen in the room, like screen the room, and ask how do you compute performance? So, well, performance can mean different things, and it can be measured in very different way depending what we want. The point we want to make here. The point we want to make here are two things. So the dwell time is just a good measure because at the end of the day, it's what we humans feel. So if I have a stopwatch in my hand, I can give you a sense it's long or short. If it's short, if it's short, it's fast. It's certainly more, well, it's certainly better than being slow. So that's kind of a very naive thing. But sometimes if you're in a very specific setting, that's all what you need. Just check that, well, at the end of the day, you're unhappy if you need to wait long. So we don't want to wait. We look at the dwell time. If dwell time is short, that's fine. This concept already breaks down if I have this concept of iteration, because true, now I want to solve maybe for longer time, and then, well, long story short, dwell time is good here, and we'll use it mostly because in all the other parts, we want to make sure that we don't run for ages. So basically, to have a reliable performance measurement, the code needs to run at least 1 second. And with this, we're sure that we run longer than some function call, latency, or whatever thing. If it runs for 1 second, kind of a rule of thumb, it's that we're timing something and we're not just timing, function call, etc. And we make sure to have this warm-up iteration because, especially in Julia, with the JIT, so the first time the code is run, it calls a function, it will take longer because it may need to pre-compile it. The effective memory throughput aims at kind of giving a different sense to the time. So the effective memory throughput is basically the effective memory access divided by the time per iteration. So now we get rid of how many iterations we run, it's per iteration. And so what we do here is we want to see like how efficient somehow we do the calculation. And how efficient is how efficient versus what. And here we compare it versus memory copy. So there is, I'll talk a bit more in the GPU part about it. I put a link to a paper that where it's not to self-advertise. It's more to, there is an explanation about what I think about this effective memory copy. So, I mean, if you're interested to dive in, you can read there, and there are like other references there. So I leave it for you. The short story is that most of the codes we write, unless it's some very specific spectral thing and we're mostly memory bounded. So most things that we do on a computer, what limits us is not to do the arithmetic operation itself. Is, well, usually in scientific computing, at least the branch the presenters come from, you want to do things with numbers. So you most likely do arithmetic operation on different arrays. And, well, to do the arithmetic operation, you need to get access to the numbers you want to deal with. All right. And this generates memory traffic. And so in, I guess, 99% of the cases, what limits your performance is not how fast the flops, how fast you can do the actual plus operation in the arithmetic unit, is you will wait on getting the numbers to the compute unit or arithmetic unit and writing it back to your global memory. And then there's a way to optimize this, to use shared memory and those things, but that's not the topic of today. Just to say that most likely, especially for whatever, if you do these PDE solvers, like stencils or even finite elements, unless you use some spectral FFTs or something that you could start to get recursion where you get maybe more compute bounded, most likely we're memory bounded. In that sense, what we need to optimize or care about is just the memory traffic. And this metric says, okay, I have a physical problem here, diffusion, that I want to solve. what's the minimal thing I need to do in my algorithm to solve it? Well, the minimal thing I need to do is to read in the known value of concentration. Then I can do my gradient and my divergence, and I need to write it back to the updated value. So the only thing I need is this NIO. It's 2 because, well, per iteration or per time step, I need to read in old values and write back new values. And then, well, this is an array, so it has a given number of, I have not only one cell, I have ns square cells, and well, a number is not just 1 byte, it's like 8 bytes if I'm in double precision, so I multiply it by 8, and then I want gigabytes and not bytes, and that's how this AF formula is. And then now, if I can get the effective throughput by dividing this A effective memory access in gigabytes. So that's effectively the minimal non-redundant memory access I'll have to do to make one iteration solving the problem. If I divide it by the execution time of one iteration, I get the throughput, so I get gigabytes per second. And this throughput, I can compare it versus memory copy, which is like the ideal, right? If doing my computation being memory bounded, I reach an effective throughput that's on the same level than memory copy, it means that I cannot optimize my code further because I cannot run faster than memory copy, assuming I'm memory bounded, and that's some other little details, but that's not the scope here. So just to know what this TF means. So this T effective, basically, if you look up the CPU or the GPU, what's the memory bandwidth? It's what one should get roughly with memory copy. And then if the number here matches that number, it means that you're squeezing out the max of the hardware. So, long story short. Yeah. Obviously, we won't work with the vectorized code. So the first thing we did here already is to make a serial loop version of that vectorized code. So I can open it. Let me close this tab, open it here, and I can open it aside the other code. So now I'll end up that, just quickly drive you through the loop version of the code, which will be the starting point for what Karsten will do now, and then all the other steps. So that's our vectorized Julia code, let's say very MATLAB Python looking like to some extent with different degrees, but that's kind of this nice high level, quickly typing in and using broadcasting to make things happen here. Doing exactly the same, but in a slightly different style is here. So nothing changed here. So the main changes is now that, well, I have only one single compute function because I got rid of the flux arrays. All right, this flux array, they're just there because I like, well, I should say as a physicist, I'm not a physicist, I like to see my fluxes there. So I can, it's a good way to get rid of since I'm not a physicist. So I don't want to see the fluxes because they're useless. They're just convenience array to have them, but they're not, I don't update them and they don't need history. Instead, I use macros, so it's just rewriting what's the flux, but using a macro, and the macro you can see it as, for those who don't know it, it's the same, kind of the same as macros in C. So it's just like, instead of being a function, it will be copy pasted before being compiled. So it would literally replace the $, so it would put the correct IX, IY, and otherwise it would just paste what's in this escape character where I call the macro here. And like this, I can still have my code that looks human readable, and the physicist who knows about fluxes could look at and be happy. But what will be just in time compiled by Julia doesn't know anymore about QX. And small note, this QX is an array, an extra array we introduced. So it introduces an extra memory write and an extra memory read when we call it. And that's exactly what we don't want since we're memory bounded. So getting rid of it is a first step to, believe me, to improve performance. Yes?
Is the advantages to do that instead of lazy arrays?
It will be because we rewrite the code multiple times later. And I believe we couldn't rewrite the lazy arrays code.
Yeah, so that's let's say that's a low-tech version. That's a version that you know that what will end up instead of @qx is exactly what you typed in here. And yeah, it's kind of, let's say it's low-tech. So since it's short and used once, we're happy with it because we know what will end up there. And that's one less problem that can occur later on when performance is no good and you don't know where it comes from, for example. So just it could be other arguments, but yeah, one could have a function, make sure to inline it and make sure the compiler treats it properly, and then it would work as well. But yeah, we don't have time to, well, something we wanted just to keep very, very raw, let's say, just not to worry about. Yeah. And then in the diffusion step function, now we have a single function where we directly update our concentration based on all value divergence of the fluxes here. With the double loop, we make sure to respect the column major order such that, well, you can try if you flip it around. I guess maybe there's even exercise to slow down because you don't access memory optimally anymore. We make sure to use, once inbound, removes bound checking, which is something that would slow down the code, but returns you a nice out of bound error. And here it could just segfault instead if I made something wrong. And maybe the important thing is that, well, now I need, since I make this all in one, so it's kind of, I do directly the second derivative here. So I kind of read values of C, make derivatives and then write them back. I have to ensure also for later on that I don't write and read from the same location. Otherwise, well, later on I could get race condition, or I can even get just data race condition, because I would, if I do the, well, depending, I could read in already updated values. And so like this, I'm sure that I read in from old, write to new location, and then I make so when I call it like before, the rest didn't change. Here I just call one compute function, and then I make a costless pointer swap. So I just say, well, now, believe me or not, C2 is C, and then it just looks at another place for it. And like this, it's a way to avoid to make like a copying thing from, yep.
Job or something. If your memory down, that's like the really optimization.
Yeah.
I believe that only have like a 0.1% slope.
Well, for some reason, well, that's a good remark, but for some reason, it's really slows down in general. So I guess it does, the general mechanism certainly does more than, so the check is just one check, but I guess it does more under the hood to, well, I guess then it enables some stack trace gathering, etc. So fair point, and nice that you, like,
and
someone follows, but yeah, it's like
it enables SIMD, and it enables to in parallel copy.
Yeah, but
so inbounds it's just the entry to do more optimizations.
But yeah, good. Thanks for notice. Yeah. So and basically that's it. So the rest doesn't change, and then the last thing would be that, yeah, now basically you can forget about this one. This was just like the vectorizer was just the onboarding thing, and now we'll start from this loop version to do the next step, which is try to get share memory parization. But this is, I won't spoil Karsten's thing. So
there we go. There we go. Camera is on. I hope it's the right one. Let's see if it's the right one. Is it the right one? Yeah. Okay, looks great. Okay, perfect. I've unmuted myself. I should share my screen. That's the last thing that's missing. There we go. Okay. All All right, multi-threading. So I will first quickly, introduce some things that you need to consider, and then you can do something on your own. The things I will go through is this multi-threading notebook here. So under parts, multi-threading, there's a file multi-threading notebook. That's what I have open here. If you want to follow along, you can also just listen for a second, but then it's listening is over. All right. So what I quickly want to go over is how do I run Julia with threads? Where are my threads running on the system? Task-based multi-threading and what you need to know about it when you care about performance. And lastly, data pinning. We just heard we are memory bound, memory copy matters, so data matters a lot. What we have to know about this for the exercise. All right, first, running Julia with multiple threads. By default, Julia starts with one thread, and you can't dynamically change the number of threads at runtime. So you cannot, in your Julia session, say, I want to change the number of threads that I have. So there are three ways. You can provide a command line argument, set an environmental variable, or in VS Code, you can put it into your workspace settings. So if you haven't done these steps, run this threads and threads function, and you don't get a weird kernel. Okay, I'm reconnecting there for some reason. So let me move over to this node. Actually, let me just go here. Right, and if you haven't done the steps yet and you run this, it should show 1 there. For me, it will hopefully show 8. And if you want to also get 8 here, do the last thing of these 3 bullet points. So copy this, Julia num threads 8, and put it into your workspace settings. The workspace settings will eventually just be a file here, VS Code settings.json, and then you just put this in, right? So once again, just preference open workspace settings is the command in VS Code, and you just put this in. And the only thing you have to do is restart the notebook kernel because, to make the change go into effect. All right, so now that we have 8 threads available, the first question I want to ask is, where are my threads running? We have a big machine. Currently, I'm on a lock-in node. I was actually planning to do it on a compute node, but somehow this is reconnecting for some reason. So anyways, let's stay on a lock-in node. Where are they running? So thread pinning is the best tool by far to visualize and control this in Julia. It's also the only tool I know. And disclaimer, I'm the main author. So the praise comes with some caveat. All right, so using thread pinning and that thread info gives you a hopefully nice overview of the nodes that you are running at. So it tells us there are 128 cores. It tells us there are 2 sockets. NUMA domains we'll get into in a second. So these vertical bars show you one socket being one CPU. So we have 2 of them, right? One at the top, one at the bottom. And then you see the white numbers, which are your cores, if you will. And these slightly gray out numbers are also running in the same cores as the upper numbers. So there's hyperthreading, if you want, enabled here, right? So these dark gray ones are just the second threads that are available in a core, right? So here we have 2-way SMT or 2-way hyperthreading or whatever you want to call it. But you might ignore the dark gray ones for the purpose today and just take the bright white ones as the cores of the system. So we have 64 cores in the first socket and 64 cores in the second socket, which is just exactly the number of cores that each CPU in this machine has. And these yellow numbers and purple numbers are the Julia threads that I have. These are my 8 threads, and they run somewhere. Maybe if I run this again, maybe they've even switched. I'm not sure. I think there was a switch up here, if I'm not mistaken. So they can migrate around. They can do whatever they want, right? The operating system can once again, move them around. All right. And that brings us to the next point. Now that I know where my stuff is running how do I influence where my stuff is running, right? Maybe I want to get rid of this randomness and of having the OS scheduler say where things are running. And why would I do that? Multiple reasons. The ones I want to mention here is, obviously, you want to avoid double occupancy of CPU cores. You don't want to have 2 threads running on the same core, right? Because then they are, sharing resources and fighting for attention, if you will. The second thing is reduce noise and benchmarks. If you have a stable setup, right, that's always the same because the threads run always at the same cores, you get more stable results. If the scheduler moves things around, right, that could influence your benchmarks. And lastly, and that will be kind of the focus of this bit here, is you can address the complexity of the system topology, which is a fancy way of saying, right? There are NUMA domains, which I'll explain in a second. And if you know about them and target them in an efficient way, you can great factors of speed up. More about this in a second. So how do I actually do it? Thread pinning exports this pin threads function. So basically, it's just pin threads, and then it takes a symbol. The options, most of them are listed here. So you can pin to CPU threads, to cores, to NUMA domains, to sockets, to whatever. And if you do that, so now I've pinned to cores. There you go. Now my threads are running up there, and they don't migrate anymore. I've pinned them. You know, pinning means stay there and don't go anywhere. So I could change this up, right? Play around with this. I could do sockets here, let's say. And now I've pinned them in a round-robin fashion to sockets, right? So the first thread runs on core 0. The second one runs on core 64. And then, you know, back to the first again. You see the entire mapping down here is specified explicitly. All right. And then NUMA, before I talk about what this is. So there are NUMA domains in the system. And what I've done here is pin threads NUMA, and then also I have given thread info a group by command. So by default, it groups by sockets. So it showed me one socket and the other socket. And now I just changed the visualization of how I, you know, print out the CPUs that are CPU cores that are in the system. So now we have 8 NUMA domains. Once again, what that is in a second. And now I see the core numbers that belong to different NUMA domains, right? So I see, you know, I don't know, 0 to 15 belongs to the first NUMA domain, 32 to 47 belongs to the third NUMA domain, and so on. And by pin threads NUMA, I did a round robin through this, right? Through these NUMA domains. That's also why I used this visualization. If I wouldn't have used it, you wouldn't have seen that it is systematic, right? I would have just pinned to some cores. But here it's obvious that I pinned to the first cores within each NUMA domain. All right, so what are NUMA domains then? So basically it's about memory, right? Memory domains. We've learned that we are probably memory bound, so we should probably talk about this. And the way clusters are set up, and I'll focus on Perlmutter and specifically, but it's true for other clusters as well, that they have more than just one memory channel and more than just one, you know, memory block in your computer. Like in your laptop or whatever, you probably have one or, you know, one DIMM or whatever. In there, they are not just do they have more, but they're also separated. They are not at the same place. They are spread out. So typically, you know, it might be that one kind of one block of memory is connected to one socket and the other one to the other or something. That's true for Intel mostly, for example. And these AMD Milan CPUs, they have, as we've seen, 8 NUMA domains, 8 memory domains. You see 4 of them here, these DIMM slots, you know, in the top right, top left, bottom left, bottom right, these DIMM slots. This is our memory. And now you say, these are only 4, right? We have 8. Well, this is just one CPU. We have 2 of them, right? We have a double socket system. So we have exactly a clone of the CPU on socket 2. So in total, we have 8 NUMA domains, each CPU having 4, okay? So even within a CPU, there are 4 different memory lanes, if you will, right? And little spoiler, if you address those and utilize all of them equally, then you can get much more out of your memory bandwidth, your memory copy or whatever, than if you just put everything on the first 5 cores, or let's say, okay? That's kind of the message ahead. All right, we'll come back to this in a second. Pathways multithreading. Okay, I should have thought about my colors here, I think. Maybe switch to a light. Let's go with GitHub Light, maybe. All right, there you go. So the thing I want to make clear here is that in Julia, you don't, semantically, you don't control threads. You control tasks, right? That is, when you run a computation, you don't say thread X do the computation. What you say is, give me a task that runs a computation and then schedule it on a thread, right? Think at spawn, for example, or, you know, at threads, which we will come to in a second. So you control the left bit. You say, these are my tasks. These are the things that I want to get done. And then the Julia scheduler dynamically will schedule them on the Julia threads. And hopefully it's good. Sometimes it isn't. And it won't be great here. And then once you have your task running on your Julia threads, right, the Julia threads are obviously running on some CPU cores, as we've just seen, right? And I've told you how you can fix the right arrows, right? Like the arrows going from threads to CPU cores, That's pin threads, right? With pin threads, can I say exactly which thread is running where? What I haven't told you yet, and we'll get to this, is how do I make a task run on a specific Julia thread if I need to? All right. Advantage of this approach, like this dynamic approach that the scheduler is free to schedule things wherever it wants to. High-level abstraction, nestability. You can nest parallel code, like parallel code is calling parallel code, is calling parallel code, and so on. Like think of parallel libraries and so on. And then you hope for the best that the scheduler manages this crowd of tasks sufficiently on a computer. The disadvantages is there's a scheduling overhead to this dynamic organizing of where tasks are running. And more importantly, there can be an uncertain and also suboptimal task spread assignment, the left part of the plot I just showed. Not only can it be suboptimal in the sense that it might not respect the NUMA domains or whatever, it can also be uncertain. You all remember, I guess, the don't use thread ID blog post, right? Because of that reason, because the scheduler might even say, your task is running here, and now it's running somewhere else. During your function, right? You wrote a function, and in the middle of the function, the scheduler says, wait, stop, I move you to a different thread, and then continues running. And if you use thread ID in this context, right? Thread ID isn't a constant across a function. That's the big problem, right? All right, anyways, that's not the main point I want to get at. How do we use threads? And I once again, focus on add threads here because that's what you will need for the example. We've saw the loop version already, right? And that's where add threads comes into play. So just to get our basics done, like add threads, you just put it in front of a for loop. I even put, you should execute all the cells. If you put it in front of a for loop, and I put dynamic here as a scheduler, you don't have to do that. It's the default anyways. So you can just write add threads. And then you see where the iterations are running. And if you run this multiple times, you will see fluctuation there. Not every iteration is running on the same thread. And maybe even some threads are doing more iterations than other threads, right? That's the dynamic nature of the scheduler deciding whatever it wants to. And now let's say I want to change that. I know about NUMA domains. I know everything. I want to use these channels that Carsten just mentioned, right? How do I tell Julia to stop this business? Don't do your dynamic stuff. I want to have a clear mapping between tasks and threads. And for add threads, the answer is just put static here. If you put static here, then what happens is that this iteration interval is just split up into n threads, many tasks. So however many tasks threads you have, you just create that many tasks. So each task here will do 2 iterations. And then it will just do the obvious thing. So the first task goes to the first thread, the second task goes to the second thread, and so on. And we can see this if I run this, that's exactly what happens. If you look, iteration 1 runs on thread 1, iteration 2 runs on thread 1 because every thread gets 2 tasks, 2 iterations. Sorry, 1 task, 2 iterations. And if you run this over and over and over and over again, you will see it will always look the same, right? There's no uncertainty there, and you know exactly what's going on. So this is one way to fix the mapping between threads and tasks. So if I use this to parallelize my loop, and now use thread pinning with pin threads to pin these threads to cores, I can control completely where, in which CPU core the thread is doing its work. Okay? Yeah. No, go ahead.
Just the behavior if you have more than fewer threads or more
Yeah.
threads than fewer.
Yeah, not a stupid question at all. So you mean for static, you mean?
Yes.
Yes. So the crucial thing that people always, so that's a great question in that regard. What people always forget when they think about threads, it chunks up the work. So I've said this, so let me say it once more. And threads always, add threads, always creates as many tasks as you have threads available. So there's no way with add threads to have more tasks than threads. It's not possible, right? You can have more iterations than threads, but what will happen is the iterations get distributed over tasks, and they get distributed in the way that you would imagine as just first, like round robin, essentially, right? So it's not smart. It doesn't balance it in any way. It's the stupidest thing. You could write it yourself in 5 minutes, right? It just says my entire iteration in round robin, distribute the stuff. Anyways, so now we've learned how to pin the left side, right? We learned how to pin threads to cores, and we learned how to get rid of the randomness that is called the Julia scheduler. Okay. All right, and now the last bit, data pinning. It's a fancy word if you want. So now I've told you you can control where things are running. So you could imagine a scenario where I just now put all my threads to different NUMA domains, right? So that's why we use 8 threads, because there are 8 NUMA domains. And we put each to one NUMA domain. Why? Because each of these NUMA domains, each of these memory domains, has its own fast lane to a memory, right? That's what they are. But now the question is, how does that work with array allocation? If I now allocate an array, where does it actually land? In which memory does it land? So that's the story I want to talk about. And you can control this explicitly. So you could, actually, there's a package that actually just extends the Julia array constructor where you can pass in a NUMA node. You can pass in NUMA whatever to explicitly say, this array should go to this memory domain, right? That's not what I'm doing here. What I'm doing is NUMA first touch, because that is an issue that is super subtle, but also cool in a way, and can give you speed ups if you know about it and do it right. So NUMA first touch is an implicit policy of, if I allocate my array, right, in whatever way, I write zeros of x or whatever Julia function, where does it actually land? And the rule of the game is the thread that first writes into this array, the position of that thread on the cluster, which core it is running on, determines the NUMA domain the array will be allocated on. So if the thread is running in the 3rd NUMA domain, and you allocate an array, the array will go to the 3rd NUMA domain. Okay, that's the rule. So first touch here is writing. Okay, touch is not allocating. Right, when you use the undef array constructor, right? That's fine. That's not touching. Touching is writing. So when you do zeros or ones or whatever. And array initialization is now our way to control implicitly where our data will land. So if I do it in serial, right, if I would just do something like this, define my vector and then fill it with random numbers, you could just use the rand function without the bang, but I make it explicit here. Then by the rule I just explained you, that main thread, whatever the main thread is, the location in the system will determine where the entire array will land, right? The entire array will land in the NUMA domain that is closest to this thread. All right. And right. And is there something else that I want? Okay, whatever. And now we come to parallel initialization. So now what I do is I initialize. So what I haven't told you yet, and that's the last bit of the story, is that even parts of an array can be in different NUMA domains. Might be surprising at first, but it shouldn't, because memory is managed in terms of unit of data, right? Memory pages. And these memory pages, so the array in itself is not one big thing, right? But it's like the element or unit of data is the memory page. And for your entire array consists of lots of memory pages. And I can use these, put some of these memory pages in one NUMA domain and some others into another, right? Looks a bit or sounds a bit complicated, but that's what the computer is doing. And knowing this, what we can do is we can initialize our array in parallel to distribute X across all NUMA domains. So what am I doing here? I'm pinning my threads to NUMA. So I'm making sure that every one of my threads is running in a different NUMA domain. Once again, I have 8 threads, 8 NUMA domains. So it's a perfect one-to-one mapping in this example. Then I allocate my vector. I don't touch it yet. I use undef. I just say I need memory in a second. And then I use thread static to initialize, to again write random numbers into my array. But by the very story we just talked about, this iteration will be split up into n threads, many tasks, right? And then the array will be filled from different threads. So different threads are touching different parts of that array, and these parts will distribute across the NUMA domains. Okay, I hope that made it clear. It's a bit subtle, but you will see this in a second. And the magical thing, and once again, you will do this in the hands-on, you will compare the dynamic scheduler to the static one and so on. The critical thing that is close to my heart, that's why it's mentioned there, I wrote a package which ran into this issue because it's so subtle. Typically, when you optimize your computational kernel, think of our diffusion step function. right? We put in inbounds there. We put in whatever there, right? Some of the fancy macros, maybe Chris's macro, you know, that is going away, sadly, loop vectorization. Typically, if you want to optimize the performance, you do it where the code is. Here, what I'm doing is I'm initializing my data differently, which happens somewhere else. And the performance of your computational kernel can increase up to a factor of 8, because you can go from one memory, a NUMA domain, to 8 NUMA domains, right? So a factor of 8, ideally, you won't see a factor of 8 today, but a factor of 8 in performance that is non-local to debug, right? Like non-local performance issue. Yeah.
As it was allocated in Flutter, for instance, with a sequential contiguous memory. Can I get it?
Yes, I'm not sure I understand the question.
Like, this is allocated a little bit different. It's using Lumino. So each part of the memory, so for instance, there are 8 elements.
Yeah.
You get one element in one different Lumino, right?
Not one element, but a chunk.
Yeah, a chunk.
Yeah.
Can I get this same array now in a contiguous memory now? But
Yes. Yes.
It doesn't matter.
I mean, you can, obviously, you can. You can move it around and you can. There are explicit tools for it. Oh, sorry, yeah. So the question is, can I get back from this, spread out across all NUMA domains array? Can I get back a contiguous one? Can I sort of tell the system I want it now all in the same memory or whatever? Yes, once again, there is a libnuma, numa.jl in Julia, the same library that is used in C and whatever. You can control this manually in a detailed way. And also in C, by the way, the same issue arises. This is not a Julia issue, right? If you would write at threads, replace this by OpenMP, parallel 4 or whatever, the same thing, right? NUMA first touch is not a Julia rule. It's a system rule. In fact, you can even turn it out, turn it off. You can also turn in NUMA balancing, that it automatically overrides that rule and whatever, right? But on most clusters, it's just enabled, and I've not worked on a single cluster where it's not just the way I described. Yes, it's just fine. It's just fine. It's just fine. Typically, it doesn't care where it lies. It is an array. In some sense, it doesn't even care where the memory pages are. You all the time work with data where you have no clue where the memory pages are, right? So it's yes, exactly. All right, 2 more questions. Okay, let me, before I take the questions, because, yeah, exactly. Let's go to the exercise, and I'll come to you, and then, get other people going. So if you open the README now, this README MD, you can either look at it in text form, or right-click on it and say show preview or whatever it is called. Yeah, open preview or something. Then you see it rendered. It's just Markdown. So these are some steps. And what you do here is, just to pitch this real quick, the loop version that Ludovic introduced, we only do minor changes to it. We parallelize the computational kernel. We parallelize, like, once with dynamic scheduling, once with static. We parallelize, we initialize our data once in serial, once in parallel, and within the parallel part, once static and once dynamic. So basically all possibilities. And then you benchmark all the stuff with correct pinning, and then you look at the performance results. That's roughly the story of this. It's written out here. Feel free to do it now. I can walk around and help with it. And I'll come to the questions, okay? No, yeah. Oh, have I? Yeah, okay. Let's talk about this in a second, what we do. Yeah. Okay. And just one more comment, as is true for all the exercises, the solution is already there in the solution folder, like the outputs that you should see or whatever. So if you are, I don't know, can't do it, or you are too lazy to run the code or whatever, you can just look at the output and reason about it, and so on. Okay, so there were 2 questions. Who had a question? Well, the plot, you have to look. You mean the plot? You can with arrows. Yeah. Yeah, it's like there's some change. You can basically, well, the string does, it just reduces one for every single animation. And then, yeah, it's not an animation, but it's a plot.
Okay.
And
Yeah, I had a question about the, asking this, the grants on the big ones, the objectives. Does that mean, I don't know, like a field vector that's assigned to a pseudo random? Pseudo random in this group.
sorry, I'm not sure I understand the question. Which example is that?
The previous slide. So this is if you do this float element end up in a different randomly assigned.
No, not random at all. That's what we call static thing. So we put static thing exactly that's not random. It's actually our situation is what we display out here. First, n whatever endless elements go to thread. The next n will go to thread 2. The next one will go to 3. So
How is n?
well, it's the length of this thing divided by the number of threads that you have. And if you have a reminder, it does the stupid thing, you're going to be filling up the first one first. Okay. So this is static. The mapping for the information space to tab and to threads, because we have static, is completely fixed. And then, so that's why it's not random where stuff like that, because it's exactly clear which parts, chunks that this narrative will be specified. So
100 divided by.
in that case, so maybe 100 is something that's choice. Sure.
It applies to the assigned range. Got it. Anyway.
That's far much.
Well,
It's here. Yeah. Before they.
so
Catch. Yeah.
and within that, there's so basically, what's assuming that non-process that they're doing by one a certain CPU space, that they're from 0 to 12, and one with that, if we're within that infinity into shared memory. No, you shouldn't. You shouldn't. Well, you can, but you should don't be. The issue here is just you have to get so you have to put either you or you can yeah. You can test it, but you won't be able to use the video with the state. Because then they'll make it that's a different time. Yeah, let's see what are we doing.
Well, I guess we need, I was writing to be honest, that well, I guess we could read reader. I need to, yeah,
Just a second.
Yes, I need to focus for really just on things. So let's say GPU and piano instances, so he can briefly introduce NPM.
Okay, yeah, if you can.
And just bring piano and go to GPU and piano, such that we have to be for days.
Okay,
That's what I was checking with you.
Can you take care of that? Like communicating with him and
Yeah.
saying when to stop. When should we stop this here?
And we have 45, they will have 45
Okay.
minutes to do NPM and GPU and piano.
Okay, yeah, let's try.
What? Just okay.
Okay, yeah, sure. All right, so there was a question somewhere. One particular assignment right. And then later you run a kernel, and then you do right. And this is what it would be against the performance of the just one. So yes. Well, yeah, that's that. I mean, we have to be so much about time. Yeah, it's good. I think absolutely. We have to go and purpose. It's a good strict. I think we have to in the next couple of years. That's right.
Is there, I mean, is it only like most sort of these, and I know I'm not going to parallel. I think what variations do that.
That's a good argument. Like typically, so yeah, so that's one critical point. Yeah, this is very fun. Small. So we are training so it's in series we are all so this will be not only the guys only the idea to basically you have a string with the for one step you know yes well not even a square the difference is if the other one's parallel the thing that will run in parallel in the sense that like it's serial on each thread, where each thread will be whereas here you have a separate serial, which will always wait for all the threads to finish doing this. So we have lots more synchronization of the and if you want to work around this, whatever. And if it's possible, that would just kind of do it function. Well, yeah, like the structure doesn't matter too much. Like, yeah, we could also like to send one. I mean, that's obviously it's special. That would be that. Exactly.
Would it just do like that, like sitting there as regards?
Well, see, I think it's really good. Actually, that's very good. Yeah, I'll try. So, it's on the morning. It's on. There's a really
Is, you know, my son is already was like just figure it so
yeah. So then
oh, I see, I see. That's right. Yeah, I feel probably right.
Well, okay, but then you have to remove the entire code and maybe I'm supposed to show you the two.
So where you have it, you just
Oh, you just write it as one.
yes, problem is you need to have the collection there for.
Yeah, okay.
Allocation.
Yeah, okay. I mean, I guess if you write it, I'm not serious about my performance. I mean,
It's not great.
at least if you have to use sophisticated. That's completely can have a chance, but that's what we're doing.
Yeah, the problem is, yeah, you need to have like collected.
But the idea is just general.
Yeah, what comes to
Well, you know, to be well, because they didn't so they the tax base family needs to go. You go that so they just chose attraction about but 10 years always message. So you know the guys are the United States, you have to tell which I mean, yeah, what is it? I didn't make it. I don't know who else, maybe 1 or 2 of
So I mean, just a little announcement that, well, although we kind of, there's certainly a bit more time needed to finish that, but just to, since everything will be up and running for the entire week, and well, that there's quite some other material, so I guess we're slowly, like in 1 minute or so, slowly transitioning to the next part, which is like going away just from shared memory parizations, so using MPI, and also doing the GPU part in the remaining 45 minutes. Yeah, just, you know, and sorry for cutting a bit short, but yeah, I guess like, you know what to do, and like you can also work through this later on.
Yes, sure. Yes, I'm wondering. Which I ran. Oh, now I did. That was very fast.
I guess maybe we can switch, and I can present on my laptop such. Yeah.
Okay. Yeah. Okay, maybe let me give a very quick outro, like 30 seconds.
Yeah. Maybe I can start sharing my screen. Just
Yeah. All right, just to so once again, we are sort of you know, as it is, you think you have more time than you have and whatever. The good news, as Ludovic says, is you can play around with this until the end of JuliaCon. Right. The only quick message I wanted to say, like not spoil too much, but what you should see eventually is, just because I've been asked this as a rule of thumb, you should see when you run these benchmarks that dynamic is almost always slower, never faster, but either on par or slower than the static variant. What you should see is that parallel initialization matters a lot. And what you should also see is you should also see that if you increase the grid resolution, which is just a way to say our arrays get bigger, our memory accesses increase, right? Like basically putting more pressure on the memory lanes, right? This NUMA effect will become more apparent, right? If the problem is super small, they might be all on par for different pinnings and whatever, none of this matters. But the bigger things get, the more we actually transfer data, like as closer as we get to this memcopy limit that Ludovic mentioned, the more this will impact. And you won't see a factor of 8, but you should see some nice factors, right? That's sort of the moral of the story, and the details either to be found in the solution folder or discovered through the rest of the week. Yeah, maybe one question and then we switch. Yes, maybe that's what I do in the script. I'm super greedy with these job scripts. Well, the limit of using the entire cluster is a bit tricky because in some sense pinning doesn't matter anymore because like you use everything anyways, but the story about the parallel initialization and the mapping of which thread is actually working on which part and is the array close to that thread or not, like this entire data pinning story still applies in that case. Yeah. But 8 is instructive because there you get, if you make the example cleaner, if you forget about all this diffusion business and literally make your kernel some memcopy, for example, just to make an extreme case, you will actually get a factor of 8 speed up. So that's why I used 8 threads and so on. Okay, but sorry for the stopping this short, cutting this short, and also the other parts, but we'll switch now.
Yeah.
So I'll stop sharing, and I will mute.
So is it my turn? Hello? I can't hear the room.
Yeah, well,
who's speaking, Johannes?
Yeah.
Yes.
You have to put your sound output, like audio, ... audio settings, and then Stresstron. Now the sound, and also in your click on here, yeah, sound somewhere, yeah, there, sound settings, yeah, that's perfect. You can turn.
Can you speak, Johannes, to see if we hear you?
Hello, can you hear me? Also, can you not keep the room unmuted and let me know when I should start?
You can start.
Thank you. You can leave the room unmuted.
Okay.
All right, I should. Can you see my screen?
Yes.
Perfect. All right, so I'm going to give a lightning introduction to MPI. That will be a bit of a challenge. So I highly encourage you to look through all the notebooks and the examples in the parts/MPI folder. And to build on what Carsten previously said, it's very important in HPC to have sometimes where necessary fine-grained control over your over the resources that you have. So if you're looking at just the CPU, then thread pinning is really important. And then when you look up, and thread pinning still continues to be important, but then as you scale up to the machine size, you also need to understand what the network interfaces are doing, what they're doing in relationship to the GPUs, and so on. And so we've started collecting examples, like there's an example here in advanced about how to select a GPU based on the HWLock layout.
Can you make larger fonts?
Oh, oops. Yes.
A bit
like
larger.
So.
A bit
Even
more.
larger.
Yep.
Okay. And so anyway, I won't go over this. I'm just going to say, look in the advanced folders as JuliaCon progresses. When you might have some downtime, and the training accounts will be available until Sunday. All right. So we're going to go and we're going to jump right into MPI and MPI communication. If you are interested in how MPI and Jupyter work together, I also recommend this MPI plus Jupyter notebook. We're going to skip that though. And so in MPI, communication between nodes is explicit. And so we're going to be looking at a simple communication example, and then how we use communication, MPI communication, for something like a PDE solver, like the explicit diffusion solver that you've all seen already. So we're going to, the previous demo is basically, this refers to the MPI plus Jupyter, but essentially the idea is we have set up an MPI communicator, and it is running on 4 ranks distributed across 4 nodes. So basically, this Jupyter notebook is running on a 4-node Slurm job. And if you want to understand how these MPI do things work, look at the section 1. I always like to run this just as a sanity check, but MPI has a whole bunch of boilerplate code that you have to use. Excuse me, a whole bunch of boilerplate code. And here you can see that we have 4 ranks. So the communicator size is 4, and there are 0, 1, 2, and 3. The order is always shuffled around, and you can see that they're different, that it's running on different nodes. Now we want to make the nodes talk to each other. Before I show you exactly how we distribute, so how we communicate, we have to now kind of put ourselves into the mindset of MPI. MPI is a single program, multiple data architecture, right? So you're running the same program on every rank, but the local data on every rank is different. Here, rank can be a different process, can be a different node. It depends on where those ranks, where Slurm has put those ranks. So something like a grid-based PDE solver, what they will do is they'll use something called domain decomposition. So you take your grid and you put a little bit of the grid over here on this rank and another part of the grid over here on that rank, and so on. Now, in MPI, for something like this, we can use the Cartesian communicator. So first thing what we want to do is we want to interrogate MPI about the dimensions. And so that's what this does is it fills a stims array here. And then we can see that all the MPI ranks agree on the dimension. So now they know the dimension. We can actually break up our domain into grids here. All right. We use Cartesian grids. For 1D, it's kind of trivial. In the hands-on example, you'll be using 2D. And 1D, it's basically just a line. But the way it works is we create what's called a Cartesian communicator. I've explained all the inputs here. And what we then do is we take the Cartesian grid and we shift it once to the left. And that then gives us a list of neighbors. And that's really important later. So this was the example. And if you now run it, you see that the chord, well, in a line, it's really just going to be 1, 2, 3, 0, 1, 2, 3. In 2D, it will actually be 2-dimensional coordinates. And then our neighbors, remember, you have a top and a bottom neighbor, right? So then our neighbors is a tuple. of the ranks of the bottom and the top neighbor in that order. And also, you might notice that we have got a -1 here, and things like this is really common for MPI. MPI uses a whole bunch of globally defined constants because it's sort of a very C-centric framework. So if you want to know what -1 is, it's actually MPI proc null. So that basically means there's no neighbor there, right? And you're going to be using that later too. All right, let's do point-to-point communication on that grid. So each rank draws a number between 1 and 100, and we want to communicate with our neighbors. That's pretty straightforward. First, we're gonna just create some random numbers. Remember, it's multiple, so single program, multiple data. Every rank will, even though it's running the same program here, will have a different value because it's a random number, right? And we can check that, and you can see each rank has a different number. MPI uses 0 copy. So if I want to send something, I first have to put it in an array called a buffer. And then I give that buffer to MPI and say, it's safe. I'm not going to touch this. It's safe to send. Right. And it's important that I don't actually send anything when there's a proc null in my neighbors. So I'm only going to copy if the neighbors are not proc null. All right. So now we're ready. Great. MPI is transaction-based. So if I'm going to send to rank 2 some data, rank 2 must be able to receive that data, and it needs to know what size of data to receive. So first, though, what we need to do is we need to also create some guards so that we can block the execution until every rank is done. And so we'll be using non-blocking communication, and then we will be using this Räss here to block in certain points. We use isend for sending, irec for receiving, and pro tip, start the receive before you send the send. Right, and this is basically what it looks like. We start a receive whenever there's a neighbor. We start a receive from that neighbor. And then whenever there's a neighbor, we start a send. And then we use the dest and source to tag the data properly so the data arrives and can get unscrambled in the right order. And really, really important, we have to block now. Why? Because my receives are going to write into buffers. If I charge ahead and look at the state of the buffer before MPI is done with it, there might be corrupt data in there, or there might be no data in there. It might also be data, right? So it's always good practice before touching our buffers to then do a wait all until we know that the buffers are safe to touch. And now we can look at what data has been transferred. And you can see, for example, rank 0 that has a random number of 38, and then rank 1, which is the next rank along, the previous neighbor is 38. You can kind of look at this and decide, well, yeah, okay, this actually is correct. Now we can put all of this together and look at how we would do this in 1D to actually solve a heat equation. And for that, we need halo exchanges. And these are bloody tedious. Anyway, the background here is pretty straightforward. You've got a stencil operator, and that operator needs the next and the previous index. So there's a width of 2 that we are going to be iterating over. So that means my local arrays have a pad of 2 around them that are what we call the halo region. Also, very importantly, and I don't have time to really let this settle, but we don't transfer at both cells. We only transfer one cell, right? So here are our 1D grids, and the second to last position gets sent to the last position, so the first position of the next guy. And the next guy's second to last position gets sent to the first guy, right? It basically, also the second position gets sent to the last position of the previous guy, previous domain, sorry. In 2D, it would look like this. Thanks to Carsten for actually making these diagrams. All right, so 1D solver example. You know this background already. So in 1D, it would look something like this. Remember, we've got a halo of 2, so we are iterating. We're not going to go all the way to the end. We're going to stop 2 from the end, and we're gonna leave a gap. We're only touching 1 away from the beginning as well. So we're basically leaving a halo around our local grid. And in MPI, I can't globally address anything. So what I'm doing is I'm going to create a local memory everywhere, and on rank 1 at position 8, which is the last position before the halo starts, I set a value. And then I can print every rank, and you can see on worker 3, and that would be, here we have our set our value, almost done here. So it's really good to work with, we're always swapping around. We have our current state, our next state, and then we swap them around. So I'm going to allocate my next state using similar, and I'm going to make sure everything is zeroed out. Where is this? Okay, and now we can do a halo exchange. Once again, we've got to send and receive buffers. And now you're going to see this big ass amount of code. I'm not going to be able to explain all of it. There's some things I want to point out. The first one is, once again, we are sending the second to last, the second and the second to last bit, and we are receiving the ends, right? So the second to last bit away from the edge, so the first halo cell is being sent, and the second one is being received. Yeah, blimey. This always goes like, I had to work on this like very carefully for like half a day to get this right, and I do this all the time. And then this is sort of the same thing that you saw before, but all smooshed into one function. And we call this the halo exchange function. In 2D and 3D and so on, this gets more and more involved. All right, so this is how the solver would then look. I'm just going to go one step, and then we can do the hands-on. But yeah, basically the way a program like this would work is you'd run your step for the solver, then you do a halo exchange on that state, and then we swap around the previous and the next and repeat. And just to illustrate this, MPI also won't give you all this nice interactivity that you have with other things like distributed. So so you kind of have to debug things like the old-fashioned way in many ways. But the way it works is on worker 3, remember worker 3 is where we had at this position here, we had our we just created one bucket with with everything in it. Now we ran one step, which then populated this and this value here. So it populated the first cell in the halo region. And then the halo exchange moved that or copied that over to the zeroth, this is the second, and this is the last. And then, so the second to last goes into the last position of the halo on the next worker. All right, so that's the theory. We can do a practical part here. The practical part is located in the MPI folder. You can look at the solution, and you can give you can try filling in the details here in the to-dos. Everything else has been filled in for you already, or you can cheat and look at the solutions. I want to also do one quick plug. Look at the distributed 0-1 distributed IPython. It shows you the same thing, but how to do it with distributed. And the nice thing with distributed is you can then plot things as you go. There are some performance differences, and there's a lot of subtleties here, but take a look at that. And there's also a version for that for Dagger. All right, how are we with time?
Yeah, well, we're good and bad. So thanks. Well, you were totally fine. So I guess, well, now there is not only for you, so it's just because, or so yeah, because we're running a bit late, and we didn't anticipate that there was such a break that was already that was planned. So yeah, workshop ends at 4:30. However, we just checked, and from like room-wise, we could run until 5, meaning people, I guess. So just practically.
Okay, so you have you have the choice between staying with us until 5
or
and dying in the storm, or leaving early and losing out on some GPU stuff, right? That's the
just
up for you to make the choice. Okay, whatever. Yeah.
Just to make some meaningful things, I guess in the remaining, so now we have like, let's say 20 minutes to do the hands-on with the MPI, and then that would be it. I mean, it's not meaningful to cut out like the hands-on. So now we get started with the MPI hands-on, and then we have, if we stay until 5, or people who want to stay until 5, we have time to do the GPU/GPU MPI part in the remaining 40 minutes, like at normal pace. I won't squeeze in this last part now because otherwise it's just useless. So, and for people who cannot make it until 5, then you have done the MPI part, and you could do on your own the MPI GPU if you can stay until, or don't want to stay until 5. I guess, well, sorry for that, but that's certainly the most fair thing we can do right now. Yeah. Well, I guess the thing is that in the MPI, so let me just pull up what to do for the MPI part, just that you see it's basically filling this update Halo thing and getting the code to run that we will need anyway for the GPU part. So that's a bit, that's only the kind of little thing.
So let's go.
So let me.
But irrespective of the storm, just to be clear, irrespective of the storm, obviously you're free to leave, right? You don't have to suffer longer here. If you feel this is suffering, then we won't take it personally. I promise.
So one more thing I forgot to add here, while Ludovic pulls up some things, is that we in HPC regularly use MPI. This is not just like a fringe thing. That's sort of the gold standard in terms of network communications. Even for GPU accelerated code, you'll probably be using MPI and CUDA aware or GPU aware MPI to handle all of your internode communication. So yeah, like this is not a tangent. This is really like on your way to running HPC code.
Right, and maybe just, I think you've done this already partially, just to pitch the code. Once again, there's a README, which contains the instruction, the solution under solutions, and so on. You've pitched that already. But what I can tell you is that the stuff that you have to implement, it's really just 4 lines of code. So basically just the I receive, just the I send, put it in there. If that's too much, or because of time you want to cut it short, copy it from the solution, and then run the stuff. Definitely running the stuff is a learning experience if you have never run MPI code before, whatever, right? If that's you, then go with running the stuff over writing that 4 lines of code.
Yeah.
I think that's more important also for what follows.
Yeah,
Okay.
Exactly. Thanks for making this clear. So yeah, the tasks are in the README, but basically the code. So if you're on the MPI folder, it's again our diffusion solver in 2D. This part doesn't change. So, and the only thing that's kind of added now is that the diffusion step works as Johannes nicely explained. The diffusion step is this local process that has, anyway, because of physics, we have this halo of boundary condition. And there we either have the physical boundary condition, and with MPI, what will happen is that we somehow cut in the middle of our global computational domain, and we'll need just to make sure that the local process, they get their boundary conditions basically from, not from physics here, but from neighboring process computed thing. That's why there's this overlap. So the physics computation don't change at all. The only thing we need is to make this update Halo function, and I guess what Karsten nicely said. So yeah, the idea here is that so it's in 2D, so we have 2 direction, and we have like 2 dimension, and each dimension has 2 sides basically. So the general workflow is that we first, so we do it we need to kind of serialize over dimension. This is to make sure that, well, one of the reasons it's pretty obvious is like if you have a 2x2 process, there is one, the cell in the middle that's kind of shared among all 4 processes need to have the correct update, and this only happens if one does serially over dimensions. So I serialize over dimension, and the first thing is to well, take the data from A, so what we want to send, the second and the one before the last. In X dimension, it's the columns, to put them into these buffers. So it's just a temporary, well, it's just an array, or here a vector, 2 vectors that will hold what we copy in there, what's gonna be sent. Then we start to the first, so why we first receive and send, so it's non-blocking, but so basically we first listen, so in every process we say, hey, something will arrive, so we listen, so we start the receive, and then we start the send to make sure that if we start the send, like if we flip it around, there is a little chance that it will try to send thing and the other process it sends to is not yet ready to receive, given that this code is executed like literally on every MPI ranks. So we first start the receive, then we do the send, and then we need to do what Johannes said, these blocking steps. So here, once we start to receive, then we send, we need to block, to wait here basically until all requests, so all send and receive operation are done before we can copy back from the receive buffer. So where we've sent thing to, we copy back it into the actual array A where we want to do, well, where we do the computation. And one little note is that why to use buffers. And well, in Julia, one could here, instead of the buffer, I could directly say, well, I take a view of my, so I could, why actually do I need this copy to step? I could, in my send receive, directly, well, point to where I want to send from the array and where I want to receive into my array with taking a view of that array. The thing is that it works, but it's not efficient because, well, internally one gets, well, it will get conflicting thing to how to optimize that thing. So, well, most likely if well, in some case when it's the part of the data that's not contiguous in memory, it will try to make many, so MPI will try to make many small messages to send basically every cell on their own message, and this will conflict with the way internals MPI works, with how Julia internals works, etc. So that's why there's an explicit buffer, such that, well, when there's this buffer, it's basically just a vector here is a continuous chunk of memory, and this can then be efficiently handled by MPI. So that's just a so yes, that's the.
I think I was lying. It's 8 lines of code, yeah, because I forgot about the Y dimension.
So if we look, I mean, I guess most likely you can look at the. Most likely you can look at the solution, and well, that's kind of how it is. So when we receive, we just need to make sure that, well, to not mess up, like from which neighbors, which request, and which receive buffer, we kind of point to, and there is a logic is that well, here it's like 1 means this is the receive buffer index direction from the left neighbor, and that's the right neighbor, and that's also the left neighbor, the right neighbor, and then it's kind of the pattern is very regular, and the same happens for the Y dimension. We'd only change that now. This is no longer a 1, but it's a 2, which means it's the other buffer. So that's the thing. And yeah, and just also, so the addition is this thing, and then the init buffer is like, well, I need to well, define these little vectors somewhere, and so initialize them here. And well, I have to make sure that in the x dimension, it's an array of size of the number of rows. So because I want the left side and the left side and the right side of my array, and in the y dimension, it's the line. So it's like the like first entry. Just to have the correct vectors in case my domain size is not squared.
If you want to talk about a solution, you could show the weak scaling. Just an idea. If you want to spoil it, I don't know.
Yeah. Well, then maybe just how to run the code. So the thing with MPI is that it's by default is MPI when you run it, like it's, I guess it's in the, so there is job script here how to run it. So in Julia, one can run MPI with this wrapper that basically just allows you to select the project. But so running Julia with MPI is basically this MPI exec is what will run. So if I define that I run for 5 minutes on one node, I have 4 tasks, so 4 processes per node on the CPU, on this entrain account. It will dump things in an output file, and well, I guess here I will make on the regular.
Right. And also on the in the reservation, you'd be using a GPU node. The reservation is only for GPU nodes.
Okay, so it's fine. Yeah, then yeah, basically that's how I can define my script, and then here what it says is just like it will basically MPI exec will know that I want 4 processes, so 4 MPI tasks, and each will launch. Then from there it's repetitive. So each MPI will kind of spread the command, and each MPI task would launch Julia, which would launch Diffusion 2D, and then it will go through this MPI initialization and figure out the topology, etc. But the long story short is that this Diffusion 2D MPI code will be literally executed n times, with n being the number of MPI ranks you want to launch them on, and then you need and then the topology will internally do the rest.
Just talk then.
Yeah. Okay. And
scaling nature. There's a question though, yeah?
Yeah. Johannes, that's a question for you, I guess. So the question is like how is distributed different from MPI? And given that distributed is somehow, well, simpler in quotes, why would I use MPI and not distributed?
That's actually a really good question. It really depends on the system that you're running on. So MPI uses under the hood something called libfabric. In the introduction to MPI plus Julia, I also mentioned that with the command mpi.versioninfo, you can see what system libraries mpi.jl talks to. So basically, MPI uses on Perma that uses the slingshot fabric. It's sort of like a really trimmed down network that doesn't have any of the TC. Think of it like UDP, but even more trimmed down. And so you can achieve much higher bandwidths because you have really low latency, because you're not going through the Linux kernel stack, the TCP stack on the Linux kernel. And so MPI really is just for sending raw data, like as close to the metal as possible. Distributed currently uses TCP, There are cluster managers that, for example, like, there's work in progress to use things like UCX if that's available on your system. On Cray systems, it is not, but on like a Mellanox network, it would be. You can also use MPI using something called Dagger. So there's ways to sort of fudge TCP-like behavior with MPI. But out of the box, distributed uses the TCP network, which is much more flexible, much more resilient. So it's easier. You can do things more easily, but you will pay performance of it because for every packet, you go through the kernel's TCP and socket stack.
And maybe as a practical comment on top of that, I would never dare in my life to start, I don't know, 10,000 distributed workers. Never, ever. That's just a feeling kind of thing. I don't know if you are that bold, Johannes.
Yes.
So if you go to some certain scale, you are? Okay, then.
I am that bold. I kind of want to maybe pull up. I have to now pull this thing up. 1 second. Is it possible for both of us to share screens?
No.
Don't think so.
All right, then don't worry. Look at the distributed, so 0-1 distributed example. There's something called the Elastic Worker Manager. And yes, you can. So the important thing here is don't use your HPC systems vanilla, like they all have a normal vanilla TCP Ethernet network in there for management purposes. Whatever you do, don't do 10,000 workers over that. That will really mess with the system performance. So if you go to the top, Ludovic, no, I've updated it. Don't worry. You can go on the GitHub page. But the point is, if we use the high-speed network, often high-speed networks these days have a TCP layer that lives on top of the same slingshot. For HPE, it's slingshot, or for Mellanox, it's whatever they call it, like Rosetta. I don't care. The point is they have their high-speed network, and on top of that, they run TCP. And on that, you can run 10,000-ish workers easily. It's perfectly fine.
Okay, thanks.
The critical word for me is could. But okay, yeah.
Don't be afraid to try. Maybe this is the thing I want people to
There's
take
a question,
away.
Johannes. Just a second.
Yeah.
Sorry. Well, I mean, it has consequences.
The question is like if the main difference is mostly the networking protocol used.
No, it's how to do it quickly. You know how MPI is transaction based? By having what's called expected communication, you can take away a lot of the buffering and all of the very intelligent and very hard to tune things that networks have to do to work because you don't know what message arrives over a normal network, right? Like you have to be ready to receive anything. With MPI, you know ahead of time what's about to be received. And so it's not just the protocol, it's the whole stack. That's why we often don't call it an MPI network, we call it a fabric.
Okay, but maybe that's enough comment on that. Maybe the weak story, because that's critical of big scaling.
So just to, as well, here I went to the solution part, but well, you can do the same not in the solution part. So assuming you have either copied or quickly did the brain gymnastic to fill out the update halo, then basically the code, now would do the same as before diffusion code. The only thing that's added in the main is that we have this couple of, well, I guess 7 MPI functions that would set up our Cartesian world and the topology that we're gonna use. And as Johannes introduced before, and then like the key thing is that, well, now in our iterative loop, we make the diffusion step, but then we make this halo update to happen such that, well, we ensure that we kind of communicate amongst processes, right? And then, well, because obviously it's hard. I cannot, well, to live plot this. There's no master process in that point-to-point communication. So what I could do is that one rank gathers results and then plot them. But here, just for simplicity, I save, so I dump output file, my array, local arrays, I dump them into different output files that are named after the rank. So there's a unique ID. This me is the rank ID, and right there. And then I have and then there is this visualization script, visualize MPI, that would, well, load the arrays and based on the topology, just reconstruct the global array and plot it. And so that's basically what I did. So if I'm now, how do I run this? It's written in the README, but it's down there. It happens. So I can, well, I'm in this MPI solution project. I can then write MPI exec. I want to execute MPI on 4 ranks. So by default, it makes the compact topology. So it will make a 2x2 on the project. I run Julia and the Julia script. I can hit enter, and then it would, well, it should start the thing. Then it says, well, I'm running on 4 processes. The dimensions is 2x2. That's my topology. And it reports the timing here. Well, timing, they're not especially, well, I don't care about timing now. I just want to make sure that my implementation is correct. So I want this, the code now will have saved these output files here, well, 0 to 3. 4 output files, each rank 1. And then I can, well, now from a Julia session, from the REPL, run this.
Also run it from as a file.
Yeah, I could include the script, or just kind of run it from here. And here it's just, well, so this, interesting. So something wrong. Something is wrong. So, well, technically, well, ideally, we want to have the circle.
In solution, you see the plot that I generated this morning.
Yeah.
Everything should be fine.
Maybe I want to point out that this is really common when you develop MPI codes. You get some weird errors like this. This might be like some halo exchange not being done correctly because of an off by 1 error. So, like, this is normal.
You say you get the same plot, the same ugly plot. Okay, then compare in the solution folder. There also is the code file, right?
Yeah.
What? I literally ran that file a few hours ago. But I mean, maybe apart from what Johannes just said, you know how many issues we faced when we set this up, like these gazillions of scripts or whatever. So yeah, okay, then I'm sorry, and I'll debug it later. Sorry? We are not selling it. Yeah, it's hard to sell, but it's also hard to not use it if you want to go further on cluster. But maybe can you show the MPI and multi-node results stack?
So, well, interestingly, this is what we want to get ideally, and
I think I know what the error is, but it doesn't matter.
Yeah, and then, well, the last thing that one kind of could show is, like, I guess in the README there is like the last part, which is, well, trying to run on, well, if I run NPI on 4 processes per node, or 4 ranks per node. So I have 1 node that I use for MPI ranks. I get these problems of 4 processes, and then it's 2x2, so I'm stuck. So,
the reservation just ended, so that's probably why you were good enough.
Great. What? And yeah, so I run on 2x2. Well, I run on 4 ranks, so it's 2x2 nodes, and I get some execution time, let's say, with some related performance. And then if I increase the number of MPI processes by here increasing the number of nodes, so I say, well, now I want to run on 2 nodes, which would make 8 MPI ranks. obviously it cannot make the square out of it, so it decides to make 4 and 2, that's 8 ranks. The reported time doesn't change. And the same if I go for 3 nodes, 12 ranks, or 4 nodes, 16 ranks, then the overall performance doesn't change, and the execution time doesn't change. While maybe one would say, oh, here I would expect, since I use more workers, it should speed up somehow. So where is my speed up? And so the thing is here, the way it's set up, it's what's called a weak scaling. So actually we don't change the local problem size, which is still the same. So it's the same on 1 rank, on 4 ranks, or on 16 ranks, which means that actually this plot here, or these results here, are good because it's this kind of close to ideal weak scaling, meaning that if I keep the local problem size the same, but I increase how much, well, I run still the same local problem on multiple ranks. Here I don't see any effect, for example, of communication. So because I increase the overall problem size proportionally with the resources, still my total wall time is the same. And that's an important concept for GPU computing and MPI, because while on GPUs, well, yes, we can see in the last half an hour, so on GPUs, per GPU, it's very sensitive. So you need to run a given problem size on one GPU such that it gets good performance. Like on the CPU with the threads, it's less critical. So you have this strong scaling. So technically you had a code that you run on one CPU on a large domain and it's slow. So if you add either shared or distributed memory parization, it would make smaller portion of codes to run on different basically CPUs or core or nodes. And then you would see usually a speed up until a point where it flattens, and then it's like the strong scaling. So with the GPU, it's kind of inverse because it makes no sense at all to run a small problem or to run a not optimal problem size on a GPU. And there we want actually to reverse the thinking and say, well, if I have a GPU, I will run on that GPU the optimal problem size for that GPU. And if my problem is larger than this optimal size, then I would need more GPUs, but then I don't want to change the size, the local size that's run on n GPUs. And then I'm interested in the weak scaling and not what's called the strong scale. So meaning that here, even though it's like fairly small domains, so to get this better, like to get a very like a robust weak scaling, one should, well, fix the code and then
I will fix the code.
And then kind of increase somehow the local problem size to something that's large enough for a core to make sure that one has no cache effects, etc. And then tune the number of time steps so that the code also doesn't run for hours, but maybe for a couple of seconds, and then do this scaling test, and then it would be a proper weak scaling with like result one could really well just trust and say something with it. Here the local problem size might be slightly small. Yeah.
So I wanted to make one more comment. Just in case this was lost, because it's actually rather important. Someone said we're not selling MPI, and I want to make sure that there's one merit that everyone understands, and that is MPI works. We try at NERSC to make distributed as robust and usable as MPI and almost as performant. But here's an important fact. On Perlmutter, for example, because of the way the system software works, you distributed and Dagger will never have the same performance as MPI, provided you can write correct and good MPI code. The other really important thing is it took us about 2 years to make distributed even work, because the vendor shipped MPI and said, that's it, you don't need anything else, right? So that's something that I think anyone who wants to use HPC, I want to stress this, unless there's a really good reason in terms of how your algorithm is structured, try to use MPI. And yeah, it would be nice if other things work as well, but we're still quite a ways out to make reliable, ubiquitous, distributed everywhere.
Yep. Cool. Thanks. Let me just. So,
Sorry. What do you mean by stay? It was this morning.
Use the now you should use the debug
That's just in
QoS.
there for your curiosity.
Ludovic, don't use regular. Use debug QoS.
I thought it was a pun. You know, we don't have to stay for the Dagger workshop.
Okay.
But, that was already this morning. So. Sure.
Presentation, there was something about using the MPI cluster manager.
Yeah, you mean interactive, sort of using MPI interactively from Jupyter? Is that what you mean?
Manager and then so there these two MPI do manager begin stuff. We're not doing this here, so I think here we're just running with MPI.
Yes.
As it was meant to be.
Yeah. So this other thing is, I mean, exactly. It's sort of you know, combining distributed with MPI for the sake of getting some interactivity back, so that we can use it in a notebook. However, unless Johannes will, you know, chime in a second and correct me, this is for pedagogical purpose, at least for now, only for demonstrating things. Right?
This is mention it, but there's MPI arrays.jl and implicit global grid.jl, which give you also some of the distributed array things back in MPI. So MPI manager plus one of those two packages will get you almost the same kind of look and feel as distributed, with as long as you're doing it correctly, not doing unnecessary communication, with pretty much the same performance. But it's you have to be very careful to not unnecessarily send data across the network.
So practically speaking, it's and also we want to share, as Johannes did with his second last comment, the current state, right? Not just where it could be and whatever, but where it is. And this is sort of combining two things, right? We just heard that distributed in itself, right, already has some issues, scaling issues and whatever. We are working on them and so on, and now we're combining it even with MPI, right? So it's getting more brittle, not less. Yeah. No, it's literally combining in the sense that the MPI processes will also be Julia workers. It's not just syntax. It's, you know, I mean, as you can see, MPI works entirely different from a workflow point of view, right? You have to initialize it, and then it's once again single program, multiple data. Distributed is not. So it's not just a syntactical difference here. It's like, and this MPI cluster managers, again, takes the processes that already exist and integrates it into the Julia pool of workers. And there's quite a bit of magic going on there. There are even different modes that you can run and so on. It's, once again, I don't know, check when MPI cluster manager has last been significantly changed or updated. You know, I wouldn't use it for production run. I wouldn't. But obviously it would be great if someone would, you know, roll up the sleeves and put effort in there. But
I think the thing to watch out for is for Dagger to become
don't have to
MPI aware, right? Like once Dagger is MPI aware, let's talk.
Yeah, I guess that's indeed a good.
Yeah.
Okay.
I mean,
but yeah, I guess that will be some.
Julian is obviously amazing, all the stuff he does. The problem is he does multiple things, right? He's also AMD GPU and whatever, right? So you only have two hands. And I don't know what the priorities are.
Yeah, but there's definitely room to improve, but so for now, like at very large scale, the only robust thing that works also not just works, that it kind of would, well, here would give you a correct image, which obviously we didn't achieve right now. It's also that it works with good performance. It's another story. Yeah, let me take the remaining 20 minutes to show you some motivate quickly the GPU acceleration thing, and then show you how we can turn these little codes into like proper state-of-the-art GPU codes, and how kind of actually the fact that now there's something called GPU aware MPI makes that there's really literally only very few changes in the code to have actually to be able to well, use multiple GPUs to run a large problem. So that's really the thing. So I could have pulled other pictures. I guess most of the, well, there's a list that's called top 500. That's kind of lists the top 500 supercomputers or servers in the world. And I guess that out of this list, like the, with I guess one exception, the 10 first, they're all GPU accelerated. So GPU is really like in the last decades now, made it from a kind of interesting idea to not use graphics units to paint, to render screens, to actually make scientific computing, and somehow started with the like wave propagation for geophysics. But the fact is that now to reach the exascale, so the fastest supercomputer in the world, they have they can generate over an exaflop. It's like, I guess, 10 to the 15 floating point operation per second. It's only possible. It's not like, well, it's nice and it does it on GPU. No, it's like, it's only possible because there are accelerators and kind of GPUs in these machines. So that's, I guess, that's a good motivation why we want actually to have tools to be able to use to run on GPU and to use multiple GPUs. We already talked about that, but like what makes GPUs attractive for scientific computing is the performance. And again, we could like go along about the performance story. Keeping the same line as before, if we're motivated by the memory aspect of the things, then basically when GPU, you can see it as a compute unit with many cores. There are different cores than a CPU, but still we drastically augment the number of arithmetic units, and kind of drastically augment also the memory lanes to feed these units, but still the memory. So the takeaway is that memory lags behind compute. So there is this kind of, we're getting kind of more and more memory bound over the time. The thing is that we're memory bound, and well, I pulled some numbers for at least the GPU is the one that's in perimeter. The CPU may not be exactly the same, but even though on modern CPU that have like these 64 cores, we're also memory bound. The only difference is that the imbalance. So if you look at the ratio versus how much we're like the flops versus byte ratio, so we have a factor of 50 or 60. That's meaning that, well, we have in this on a GPU like this Tesla A100, that's the GPU that's on perimeter, we can do 50 floating point operation for free before starting to feel the fact that so on two numbers we can do just dumbly add plus minus 25 times, make that the compiler doesn't remove it, and then we'll start to become memory bound because we don't access other data, we just increase the arithmetic intensity. The thing is that kind of to look at is just these numbers. So why GPU are more interesting in general is because, well, they have a higher memory bandwidth and they can achieve higher arithmetic intensity, and that's it. So there's like well, factor between 1 and 2 orders of magnitude, and that's the speed up you expect from porting, like from making a code to run on a GPU with some, well, assuming that you have well, that you do it like that the code you're working with, or the algorithm works nicely, like can be ported and nicely parallelized on GPUs, which is not the case for everything, and that's a bit the challenge, and that's why finite differences, iterative, explicit methods are ideal, because it has this, you can imagine in 2D, my 2D Cartesian grid really looks like pixels on a screen, and so still the GPU works under the hood like to paint pixel on screen. So they didn't change much the design. They had added features, but that's it. So here I won't touch this, but it's there just to motivate a bit why we care. And I would rather just run a little benchmark to actually that everything what talking is not just hopefully blah blah, but also makes sense. So here we just kind of try to see if indeed on the GPU. So here I'm on the GPU node. If I run a memory copy, and then I run a Laplacian, and then I query what the hardware tells me that my performance should be, and then I list them all, and then just to see where we are. So that's what I'm doing now. So I'm using CUDA, which is the way to use NVIDIA GPUs that are on perimeter, benchmark tools to benchmark things, and the print to print. Then I have this function, which is memory copy, and well, I can use it to introduce the kernel. So on the GPU, so you can see the GPU as shared memory parallelization on the GPU. So the GPU is like, from the memory point of view, is like being on a node where you have the CPU and the RAM, and all the cores, meaning all the threads, which are not the same, but all the threads of the GPU, they have access to the main GPU memory, like your CPU cores or threads have access to the device RAM. And the only difference is that on the GPU, we don't care really about these cores, because these cores, they're not directly mapped to threads. So we only care about, let's say, the threads. And the cool thing is that these threads, they have unique IDs, and this is what we can retrieve here. So what we can say, you can imagine we have our 2D grid. Every entry of the grid has a different IX, IY. And now if I map these different IX, IY to a different thread on the GPU, and I run that script, and the script will be launched, this function, when it's launched on the GPU, it will be sent to every thread, and every thread will retrieve its unique IX, IY index that's different with this function that's given by CUDA, the programming layer to the language layer to program the GPU. Then I will perform this copy from A to B plus adding 1. I will perform it. I will perform it in parallel, like literally every grid point on my 2D domain will get assigned a different thread and will run this A equal B plus 1 fully in parallel. And that's how, well, and really the fact comes from that there's as many threads as grid points. And it's not like, oh, I have 2 threads and I need to split my 1000 by 1000 domain in 2 domains where I still have serial processing of 500 grid points per, let's say, OpenMP or shared parallelization task. And this is, yeah, and given that, so you see also that it's fairly close to the loop version. So another way to see it is it's like having a loop code, like with these nested loops, but where I replace the loop over spatial dimension by this vectorized index that I get from CUDA. Since I don't have a loop anymore, I cannot do the range checking of my arrays on the loop. I need to do this if check. So, well, this is launched on any thread and is mapped to my 2D Cartesian domain. So I need to check if I launch more resources than I have the grid points in my array, if the IX, IY returned goes beyond the bounds of my array for specific workers, I should just exit. Otherwise you segfault or run out or hit wrong memory thing. Then I can do the same. So here it's Laplacian kernels. So it's like just plain very similar to what we have in the exercises, but so I have the derivatives now, and while making sure that, again, like I need to skip the first and the last, so I skip 2 at the end and then shift everything in the middle. That's like how it was in the loop version. Yeah, and that's kind of the Laplacian now, where we actually saw what that would have the same results. That's the diffusion step, basically. then one can test the performance. So as we were saying since the beginning, I want to run now on a large domain, so on kind of 16,000 by 16,000 roughly, because I need this GPU. They have 80 gigs of RAM, and to actually squeeze out the performance of the device, you need to feed it enough work. Otherwise, it will be partially idle, and then you don't have a good you won't see like properly what it can do at best for the performance. So I need to use large arrays, and then I can fill them with CUDA. Instead of rand, I say CUDA.rand. This would kind of allocate it on the GPU, and I need to specify the precision. By default, it's float 32. Here, I want to do everything in float 64, so in double precision. Then I need to specify my launch configuration. So how that's internals, and there is info in the later on, but that's kind of how I map. So threads are in blocks, and blocks make the grid. But long story short, that's the optimal one, and it's written later on. The important thing is like how to run these functions. So now this function, I run them, I use this at CUDA. So this is just my function. If it was a CPU function, I would just launch it like type the function name and the arguments I pass to. Now, to run it on the GPU, I need to specify, that at CUDA says, that's going to be a GPU function with some special processing, and then pass the number of threads and blocks. So just basically how many threads I want to use, and threads times blocks would be equal to nx and y. That's what it says here, right? So kind of define an optimal number of threads per block, and then make sure that it covers my nx and y. I synchronize, so that's the same. So the function, the GPU kernels, if I call them, then I need to make sure that before, here, for timing, if I don't synchronize, it would time the host side of the launch. So it would just time how much microsecond the CPU took to launch to tell the GPU to do something, and not actually wait on the GPU results to be computation to be done. That's why I need to synchronize. Then I can use this elapsed, that's from benchmark tool, that would run a bunch of time do the benchmarking, like statistics, and gather statistics and get the minimum execution time, so the best execution. Then here it's the formula for this effective memory throughput for the memory copy and the Laplacian. And then, here I just put in, or Ivan put in, that one can try to use to query some device internals to get what would be what the hardware tells what could be given on the bus with clock rate, and this rate multiplier just kind of gives us the theoretical peak performance. And then we print it, so that's what we see. So the but if you Google the NVIDIA A100, the one that's in Perlmutter, they announce it with 1.5 terabyte second of memory throughput. That's what our theoretical prediction returns, so 1,500 gigs per second. The memory copy, so only copying like A to B, runs at this 1,300. So there is some overhead, and I guess there's certainly little things one could, in this very naive memory copy code. Yes, there's not much one can optimize, but indices are are integer 32 bits, and there's some conversion going on, and some is also not fixable here on the fly, but something that CUDA needs to be addressed in Julia. But roughly speaking, it's like fairly close to the theoretical throughput, and the theoretical throughput is really a theoretical calculation. So I mean, I guess usually even the C or C++ examples, they would also not run at the theoretical peak.
If I may interrupt, it's even worse. If you use CUDA memcopy, like the one that CUDA provides,
there
you get the same number. You don't get 1,505.
So
NVIDIA themselves.
So that's what I was saying. Like if you have a robust memory copy, that's the way to assess what's the peak is, and the delta is just the difference between like real life and theory.
In the interest of time, I think we have to come to an end. Maybe I want to show that.
But the key message here is that the Laplace. So this is not doing anything, and this is solving like basically diffusion equation, and this runs at 97% of memory copy only. And I guess this is a good point just to show like why it could make sense to do computing on GPUs, because you can solve physics as 97% of copying memory at rates which are like 2 orders of magnitude higher than CPUs. It's kind of somehow the bold thing. And then the multi-GPU thing is like, how now the supercomputers, they have like thousands of GPUs. How can I access them? Well, for now, what everyone does and the robust way is to run MPI, and then somehow to use the MPI ranks or the unique ID from MPI processes to map to GPUs. And so that's the procedure. It's also in the code. So we want to, we have the MPI, the topology knows about all processes, then we can use the shared type, so to split on groups of processes that are on a node, and on these nodes, if they're all the same, they will have, let's say, 4 GPUs like on Perlmutter, and then we can use this local rank to just say, I know that I'm process something out of all my MPI ranks, but on that node, we are 4, and I'm 0, you're 1, 2, 3, and then 0 gets GPU 0, 1 gets GPU 1, and that's really this line how you get the GPU, the device from the local rank. And had a little example that I also put on the GitHub where you can run a script that implements that, and it would return like on 4, that's on the Perlmutter, so 4 MPI rank. The local ranks here are the same as the global rank since I'm only on one node, and then I query the device. And and maybe since, just this part here is also just, as I said, like that there is what's called GPU over MPI, which is also enabled on Perlmutter, that our MPI code, the only change, so let's maybe go to just for the last 2 minutes, just go to the diffusion MPI. So just to comment on the code that's in the solution to have the one. So that's now the code we're used to from the loop version to the MPI to the GPU version with MPI. But again, here nothing changed on the physics. The only thing is from the loop, from the CPU version, I have no longer this double nested loop, but I have these indices, and the range checking is done like this. Instead of having those as my loop from 1 to size, it's now as if statement, because this code is replicated on every GPU threads. So it's not a loop. There's no master thread that can handle ranges. This function, I called it now kernel, and I call it from a wrapper function such that this diffusion step function is the same as the CPU one. It's just like internally it would call this kernel. That's usually, I guess, if you look up Julia GPU code, it's mostly done like that. Also to have this kind of same signature here. But again, that's like in the memcopy example. So I also have threads and blocks and not CUDA. And the nice thing is that our update halo is literally unchanged, meaning that now A will be GPU arrays and buffers need to be GPU arrays or vectors. And so the only change is in the buffer, where now I need, instead of having 0 of like initializing zeros, I initialize zeros, like vectors of zeros on the GPUs with correct precision. And that's it. So it's kind of only this. And then actually to my update halo, I can pass GPU arrays. And this GPU over MPI would know where to fetch the data to send it, and it would directly send it from a GPU to another GPU without making a copy on the CPU and then making CPU-based MPI like it's used to be done, maybe even, well, not so long ago. So, I mean, this is really nice because basically you can check and diff the codes and run them, but the only thing that's different from, and I mean, this code you can really, if you have like if you can do a hero run on parameters, so I can take that code, launch it on, I don't know how many, they have like 15,000 or 20,000 GPUs. So you can, if you run this on as number of MPI ranks to fill the whole machine, this code would run the local problem sum on each GPU. And there is like, the only thing you can do more in this machinery is, well, to add maybe more, well, some physics to save the world and not diffusion equation, but well, maybe one can save the world with diffusion equation, I don't know. But yeah, so that would be the only thing. And I mean, I'm stopping on that for the matter of time. But yeah, well, maybe sliding into closing remarks, and I'll start and then I leave over to you. Well, first, thank you for staying on until here. Second, we apologize for the delay, and like I guess we had too many things that we were excited about to want to show you. But the good thing is that all is there. We'll take care to fix the MPI example that was working this morning, and yeah, you can quietly work through the things on parameter until the end of the week. On most modern HPC systems, while getting Julia to run, and then things are not restricted to parameter. And maybe most important, we are around until Friday late night, and some even on the hackathon on Saturday, so that, well, don't hesitate, like ping us, or like if you're working on it and have questions, like I'm happy to, well, take a coffee break with anyone and discuss things further if that's of interest. So yeah, that's from my point of view.
I think there's not much more to add, so let's probably leave it at that. We dare you to try. I don't know, like maybe Johannes will scream at me in 2 seconds, but I don't know what the restrictions for these training accounts are. Find them. That's, you know, I don't work at NERSC, so you know, I don't know, try to get as many GPUs as you can. It might just be that your job doesn't start, but yeah, play around. And that's it for me. So Johannes?
Really quick PSA. When you log in, you see this little text that says this is a government computer. So yes, we dare you to try, but in good faith. If anyone goes and starts mining crypto, I kid you not, the FBI will come looking for you. So don't do anything in bad faith, but everything that's in good faith. See how big a job you can get, or try out a new algorithm. That's great. Please do. HPC is for pushing the envelope and exploring new things.
All right, thanks.